So I would just give a small introduction about Dr. Walt, and then we will be starting. So very good morning to all of you. Today we are here to have this workshop, a very focused workshop on space and defense technology. And this being a workshop on space and defense technology, I think no other than AESS President will be the best person to inaugurate this workshop as well as deliver a keynote address. So Professor Walt Downing, he is going to talk about small satellites for deep space missions. So you see, it is a contradictory. First of all, they are small satellites, but they are going to be used for deep space missions. And I will take few minutes of yours in just introducing him. One second. So friends, Dr. Walt Downing is the president of IEEE AESS 2020 as well as 2021. And he is the executive vice president and chief operating officer of Southwest Research Institute, SWRI, in San Antonio, Texas. SWRI is an independent, not-for-profit organization conducting contract research in the physical sciences and developing innovative technologies for the betterment of humankind. Since its founding in 1947, SWRI has grown to be one of the world's premier applied research and development organizations. Walt joined SWRI in 1979 as an engineer, initially working in the field of automated testing of aerospace systems. He expanded his technical program area, and in 1981 developed an avionics and support systems section. Recognizing the unique need of military customers who must manage systems through technology insertion, Walt grew his section into a department in 1988 and in a division in 1994. When he was appointed Vice President of Aerospace Electronics and Training System. Walt moved into upper management in 1998 when he was appointed Executive Vice President and became a member of SWRI Board of Directors. In 2016, Walt was recognized with the additional title of Chief Operating Officer. Walt is an IEEE senior member and IEEE ABET Engineering Program Evaluator and a member of IEEE Eta Kappa Nu Electrical Engineering Honorary Society. He serves on the boards of Governor of IEEE Systems Council as Vice President of Technical Operations. He also chairs the IEEE Central Texas Section Joint Chapter of the Systems, Man and Cybernetics Society and AESS. Walt is active in a variety of civic organizations as well as non-profit groups. He is on the Industry Advisory Board of the College of Engineering and the College of Business at the University of Texas at San Antonio and is a member of Board of Trustees of St. Mary's University. Walt is a graduate of Southern Methodist University, University of Texas at San Antonio, MBA he has done from there, and his executive certificate in management and leadership from University of Texas at Austin and MIT's Sloan School of Management. He is a registered professional engineer in the states of Texas and Florida. So welcome you again, Dr. Walt Downing, for accepting our invitation. And I know this time is going a very odd time for you, but still joining with us. Thank you very much. And I will pass on you the ball for sharing your presentation. So here you go.
Thank you very much. Okay. So let me see here, find that, I think this one here. There we go. Very good.
Yes.
So it's a great pleasure to be able to be with you this morning and to talk to you about some things I find very exciting, and that is CubeSats for deep space missions. The inspiration for my talk was a three-part series on the Artemis 1 CubeSats. Artemis 1 I'll talk about a little bit more later, but it's the mission, it's a test mission of the U.S. Space Launch System, the Heavy Launch Expendable System that's intended to carry astronauts to the moon in the future and perhaps other deep space missions. But in addition to that primary mission, there are 13 CubeSat satellites that are being carried as secondary payloads on the Artemis 1 mission. And in our IEEE AESS Systems magazine, we did a special article or special series, 3 magazines, on the various CubeSats that are going to be flown on Artemis 1 in April of 2019, September of 2019, and March of 2020. Systems Magazine is a benefit that you receive as being a member of the Aerospace and Electronic Systems Society. You get it in hard copy form, and of course it's also available through our resource center. So let's talk about small satellites in general. One way that satellites are characterized is by their payload mass. And once a satellite gets below somewhere in the area of 500 kilograms, they're typically referred to as small satellites or small sats. And then as you go down from there, you can see they use sort of a similar sort of classification that you see for things such as computers, mini computers, microcomputers, or technology, such that a microsatellite would be in the payload range from 10 to 100 kilograms, a nanosatellite perhaps 1 to 10 kilograms, and so forth. CubeSats, which we're going to be the topic of discussion more, are a class of nanosatellites. So they're satellites in the 1 to 10 kilogram range. Small satellites in general are intended to reduce development and launch costs because, it's very expensive to launch higher masses into space. Because they're less expensive and lower development costs, it facilitates the ability to use satellites in constellations or swarms. So rather than expending a lot of funding to develop just a single sensor on a very large satellite, you can develop less expensive sensors and employ them on a swarm. And I'll show you some examples in a little bit. There are technical challenges for smaller satellites that include limited power. Because the mass is limited, you can't carry as much battery power or any other type of power. And of course, propulsion is a problem as well. So there are certainly technical challenges. Nevertheless, the era of small satellites in general and CubeSats in particularly have enabled universities and others to conduct space research, and you can also use these small satellites to demonstrate and mature new technologies for space exploration. Now, these are often carried as secondary payloads on larger missions, and some occasionally have been carried up to the International Space Station to be deployed from the space station. But because of the lower costs, it does actually support private space flight initiatives, and this is now a very rapidly growing development of the satellite launch industry. So let's move into an example of a small satellite. In this case, it's not a CubeSat, but it is a small satellite in the 40 kilogram range. It is the Cyclone Navigation Satellite System, or CYGNSS, that was launched in 2017. It is a constellation of 8 microsatellites in a low Earth orbit constellation, and the purpose of this satellite constellation is to observe storms in the Gulf of Mexico, the hurricanes that we experience quite often during the summer in this part of the world. It utilizes a technology, a Doppler mapping technology, that can see through the clouds and measure the wind speed at the surface of the ocean. And so it's with this constellation of satellites, you're able to get frequent observables over the storm area. This mission is being led by the University of Michigan, but the partners are Southwest Research Institute, Sierra Nevada Corporation, and Surrey Satellite Technology. You can see the size of these satellites. Again, I mentioned it's an 8 microsatellite constellation, and these are the 8 satellites installed in the launch rack that will go inside the fairing of the Pegasus rocket. Now, the Pegasus is an air-launched rocket that was developed by Orbital Sciences Corporation and is now built and launched by Northrop Grumman. When it's released from its carrier aircraft, it's at approximately a 40,000-foot elevation, and it's capable of carrying small payloads up to 400 kilograms into low Earth orbit. Pegasus is advertised to be the world's first privately developed launch vehicle and the first air-launched rocket to place satellites into orbit. So again, being able to have capable satellites in a smaller mass enables even private spaceflight opportunities. I would point out that Cygnus was recognized by the AIAA as the 2017 Small Sat Mission of the Year at the annual Small Sat Conference in the Utah State University. So here's the block diagram for Cygnus, and this is very typical of a small sat. You have the control and data telemetry system. You have the structural, mechanical, and thermal system. You have the electric power management system. You have attitude, determination, and control, and a single instrument. These satellites don't necessarily carry many instruments. It might just be a single instrument. In this case, the single instrument, the single scientific payload is a Doppler delay mapping instrument, and that is the function of this particular computer. But things are important. For example, it is again up to 100 kilograms. It's a microsatellite, and the bus itself was selected by NASA for their Rapid Force spacecraft catalog. These satellites tend to be solar powered, and you need a peak power tracker. The command and data handling system is usually a single board computer with the data handling as well as the telemetry interface. For the low Earth orbit type missions, they typically utilize an S-band communication system to transmit data to and from Earth. They use very simplified and typically single self-contained units for attitude, determination, and control. You can see in this case, it's got a 3-axis magnetometer, star tracker, sun tracker, 3 reaction reels, and 3 torque rods. So it's a fairly capable attitude, determination, and control system in a single package. And so it uses emerging small satellite components and technologies at much lower cost than standard space-rated components. You can see the size of the observatory in centimeters here, 160 centimeters in length once the solar panels are deployed, and only 22 centimeters in height and 51 centimeters in width. So in each observatory weighs approximately 29 kilograms. Here's an artist's conception again of how the observatories are stowed with the solar panels folded to fit inside the Pegasus, and there's sort of an artist's concept of the satellites being deployed from this launch stack configuration after they're in orbit. The platform itself was developed by Southwest Research Institute, and one of the things to note on small satellites is you don't have a lot of options with respect to where the instruments and computers and solar panels and all that are located. And so space is a premium, weight is a premium, and also you have to consider many trade-offs with respect to the scientific mission, where the instrument has to be pointed in the correct direction to make the scientific observations that are necessary. But at the same time, the solar panels have to be correctly pointed toward the sun, and the telemetry system has to be pointed to the downlink. So essentially resolving all of those conflicting constraints in a small package becomes quite challenging and often requires some maneuvering. But again, since the weight is limiting, you don't have many options for maneuvering. So it causes quite a systems challenge in design. This was the command and data handling subsystem that was used in Cygnus. It's a single board computer with a CCSDS interface. It's very low power, high performance for small satellites. It has enough memory to store about up to 8 hours of data before it needs a downlink, and it utilizes a spacewire interface to communicate with the scientific instrument. One of the things that's important in space flight and in satellite flights is that you should, whenever possible, use instruments and controls with the proven flight heritage. In this case, the Leon architecture that's used on the Centaur board has a heritage from several previous missions, as well as the CCSDS interface having heritage from other instruments, and that helps reduce the risk of applications of these computers on missions. And again, the electrical power tracking subsystem is very important. And so one of the things I wanted to point out is that just as this talk was inspired by the AESS Systems Magazine articles on CubeSats, several of these components and buses that I'm describing in this talk are out of the IEEE Aerospace Conference, which is one of the flagship conferences of the Aerospace and Electronic Systems Society. So for more information on this electrical power system with its peak power tracker, you can refer to the proceedings of the 2017 IEEE Aerospace Conference. But just like the computer, the power system has a significant flight heritage, which helps reduce the risk. Simplified attitude determination and control. There's no active propulsion on these. They use strictly reaction wheels and torque rods. And they also used a technique called differential drag maneuvers to achieve the satellite spacing of the constellation after separation from the Pegasus deployment model. So again, with the limited size, weight, and power, you have limited options in terms of what you can do for attitude determination and control. And so you come up with some clever techniques. The satellite itself is a 3-axis stabilized platform pointing, a nadir pointing, the instruments pointing toward the surface as it flies in this low Earth orbit constellation. Now, the satellite bus that was used for Cygnus is reused in other configurations. The next mission that is planned for this bus is a NASA Small Explorer mission called PUNCH, which stands for Polarimeter to Unify the Corona and Heliosphere. This is a 4 microsatellite LEO constellation. They're a little bit larger. These are up to 4 kilograms each. One of the imagers, this one here, will carry a narrow field imager, and the other 3 satellites are going to carry wide field imagers. They are solar type missions, and the launch of this system is planned for 2023. And this mission is being led by Southwest Research Institute with support from the U.S. Naval Research Lab and RAL Aerospace. So moving on from small satellites, I talked about small satellites first because many of the technologies and components that are used in these small satellites are applicable and essentially the technology enablers for CubeSats. So what are CubeSats? They are a class of small research satellites, spacecraft. They fall in the nanosatellite family, that is between 1 and 10 kilograms, and they are built to standard dimensions or units, U's. One unit is roughly 10 centimeters by 10 centimeters by 10 to 11 centimeters, roughly cube-shaped, which is why they're called CubeSats. And then building on these units, they are modular such that they can be deployed in a 1-unit configuration, 1U, right, like this right here, 2U, where you have 2 units stacked on top of each other, 3U, and this illustrates a 3U configuration right here, 6U, where you would take 2 of these and put them together, and up to 12U. But once you start getting up to this range in size, you're typically 1 kilogram per U, so you start to get over this 10 kilogram level, and it's really about the limit of what you're going to achieve in a CubeSat type configuration. CubeSats, like most small sats, are typically flown as secondary payloads on larger missions, such as this Artemis mission that I'll describe momentarily. They're dispensed from launch systems along either rails or tabs in a spring-loaded deployer. So they don't have, again, they typically don't have propulsion of their own. They're mechanically loaded and mechanically dispensed from the from the launch vehicle. You can find a lot more information about the CubeSat launch initiatives from this website because since NASA and other space agencies are often flying larger lift vehicles, there's frequently opportunities to carry along these small satellites as secondary payloads. Here's some background and history on CubeSats. The specification for CubeSats was first developed in 1999 by California Polytechnic State University and Stanford University, and they were originally intended only for low Earth orbit missions of short duration, and the intent was for scientific research and to explore new space technologies. And consequently, academia accounted for the majority of the early CubeSat missions. And you can see the progression from 1999 to the present, a very, almost like, I guess you should say, like an exponential growth in the popularity and the number of these CubeSats that have been launched since 1999, now over 1,200 CubeSats as of January of this year. And they are no longer strictly academic. They are becoming used for serious scientific missions. And in 2018, the Mars Cube 1 or MARCO mission became the first mission to launch and operate CubeSats beyond Earth orbit. They were carried on a mission to Mars and used as communication relays for the primary mission. And here's a photo of one of the MARCO CubeSats being prepared for the mission at the JPL laboratory. So moving on to the Artemis 1 mission, which I said was the primary topic of this talk. It's formerly the exploration mission, and the primary mission for Artemis 1 is an uncrewed test flight of the Orion multi-purpose crew vehicle to test it in a flight around the moon and back. It'll launch from the Kennedy Space Center Launch Complex 39B. It's a 3-week duration mission with a translunar injection to spend 6 days in distant retrograde orbit around the moon, return to Earth, and recovery in the Pacific Ocean. So that's the primary mission. But then it's carrying 13 6U CubeSats as secondary payloads, and these were all selected in various forms by NASA. 7 of them were selected by NASA directorates. 3 of them were selected in sort of a quest challenge. They were winners of a challenge competition. And 3 of them are being provided by international partners. So 1 by the Italian Space Agency and 2 by the Japanese Space Agency. And I've noted here on the slide with these little symbols the month and year of the issue of Systems magazine that each of these missions was described in greater detail. So again, if you go to the AESS Systems magazine, you can read more about each of these missions. But it's interesting, several of these missions are involving the search for water or ice on the moon, such as Lunar Flashlight, Lunar Ice Cube, Lunar Polar Hydrogen Mapper. There's a mission, this BioSentinel is a mission that's looking to explore the effect of radiation environments on DNA. And this Near-Earth Asteroid Scout is looking at using essentially a sail-type propulsion mechanism to carry a CubeSat on a near-Earth asteroid mission. Skyfire is looking at another propulsion-type technique, as well as the Cislunar Explorer. The Cislunar Explorer is actually going to look at a soft landing on the moon, and so forth and so on. So a lot of very exciting missions. The CUSP mission is the one we're going to talk about a little bit more. This is the CubeSat to study solar particles, and it's a mission that's being led by Southwest Research Institute. The launch system, the launch vehicle for this Artemis 1 mission is the Space Launch System, or SLS. That's a large heavy lift vehicle, and it's going to be used by NASA for its deep space exploration. But what I want to concentrate on is this little segment right here, because this is the area that is used for deploying the CubeSats as follows. So here's the same, let's see, go back here, save diagram. You can see here's the Orion Space multi-crew vehicle. Here's the stage adapter and the interim cryogenic propulsion unit inside. So inside this stage adapter, there are mounting points for the 13 6U CubeSats right here. And so this is where those 13 satellites that I described earlier are going to be installed, and it's from this stage adapter that they'll be deployed en route to the moon. Here's the mission map for the Artemis 1 mission, and the colored lines represent the primary mission, where it is launched, goes into orbit, then out of orbit goes into a translunar insertion to the moon, into a distant retrograde orbit for several days, exit lunar orbit, return to Earth, and splash down in the ocean. But notice this interim cryogenic propulsion stage, after it's given the boost of the Orion on its path to the moon, it continues on, and that stage adapter is, of course, attached to it, and so your CubeSats are going to continue on as well on a trajectory toward the moon, and the propulsion stage is going to go on beyond the moon into deep space disposal so that it doesn't return to Earth. But at these points along the way, labeled A, B, C, and D, it will deploy various of these CubeSats depending on the intended mission. A little bit more about that later because there's been a change in plans on that deployment. So focusing on one of the missions, CubeSat mission to study solar particles, or CUSP, this was one of the feature articles from the April 2019 issue of Systems, and much of the information from here on in the lecture comes from this article. So I want to thank Dr. Mihir Desai for his assistance. Mihir is the principal investigator on the CUSP mission, and a lot of help from other team members at Southwest Research Institute, along with contributors from NASA Goddard Space Flight Center, as well as the NASA headquarters and the Jet Propulsion Lab. So what is CUSP? CUSP is a Science Mission Directorate-sponsored heliospheric science mission. It was selected in 2015 to be launched on Artemis 1. And the interesting thing is, at the time, the plan was to launch in 2017. But there's been, of course, many delays since that time, as additional works had to be done on the Space Launch System. So now we're looking at possibly a 2021 launch rather than 2015, which has caused some difficulty with maintaining momentum in the mission. The purpose of CUSP is to study space weather research by determining proton radiation levels during solar energetic particle events and identifying superthermal properties that could help predict geomagnetic storms. Secondary purpose is to increase the technical readiness level of interplanetary space weather instruments, and therefore it's a pathfinder for future interplanetary, that is deep space and space weather CubeSats. Now, what is space weather? Well, space weather are these events, and then you can watch this coronagraph here over the course of 2 weeks, and you can see the activity of the sun and in various solar flares and events that generate solar X-rays and solar energetic particles, but not all of them lead to these major coronal mass ejections that can be so destructive to radio communications, navigation, and electric power grids. And we don't understand this phenomenon very well. And so we would like to improve our ability to, you could say, predict space weather, or at least be able to predict severe space weather. But the analogy is if you're trying to predict solar weather or space weather with the satellites that we have right now, it would be like trying to predict the weather on Earth with maybe just 1 or 2 weather stations. So ultimately, in order to understand this better, we will need many more space weather satellites, and that's where something like a small sat or CubeSat can be quite valuable in terms of being able to perhaps deploy more of these so that you can get a better temporal understanding of space weather. So here's what CUSP looks like. This is actually just a physical model of it. I'm standing with it here in the lab, and this is with the solar panels deployed and with the patch panel for telecommunications deployed as well. So it's after it's already, what it would be about the size of it when it was after it was launched and deployed, along with the magnetometer up here as far away from the mass as you can get it. So you can get an understanding of the size. This satellite's a little bit different than other types of CubeSats in that it does actually have a cold gas thruster. Most of the attitude determination control is being done by reaction wheels, but it does have a cold gas thruster for inertia shedding. But otherwise, it's very typical of a CubeSat. It has deployable solar arrays and batteries. Differing from a low Earth orbit CubeSat, it uses a X-band transponder for the telemetry. And another thing that's unusual about CUSP is that it actually has 3, not 1, 3 scientific instruments that are quite capable. They are a suprathermal ion sensor that's being developed by Southwest Research, a miniaturized electron and ion telescope being built by the Goddard Space Flight Center, and a vector helium magnetometer being built by JPL. Now, all of these instruments have previous spaceflight heritage, but in much larger form factors. So the challenge has been on this mission is to take these very highly capable scientific instruments and reduce them in size, weight, and power so that you could fly them within a 6U CubeSat configuration.
Dr. Downey, can you just explain about this helium vector magnetometer?
Actually, that's not my area of expertise, but again, I'm sure it's being built by JPL, and you can probably get a bit more information from the article, or perhaps here's some of the specifications for it. So I would refer you to the article, but I personally don't know that much about the instruments themselves. But what I do want to say is they are very capable instruments. They leverage a heritage design, and therefore you can have very minimal non-recurring engineering and have a very high technical readiness level. But it's a very short mission. It's only a mission of several months in duration, 3 months in this case, and therefore you can have significantly lower hardware costs. So even though you're in a more severe environment, the satellite does not have to last very long, so you achieve some very significant cost reductions. So these lower costs and higher risks are very typical of CubeSat missions. We say more bang for the buck if you're from Texas like me. So what I would like to point out is that, again, the resource characteristics, very high performance at very reduced size, weight, and power. These are the three instruments. So look again here. The total mass of the three instruments is only about 3,000 grams, 3 kilograms. Very low power. Typically looks like combined they use maybe about 3U of the 6U. And so again, very, very small, very highly capable instruments in a very small package. Here's the nominal mission as it was planned. There's been some changes, but nevertheless, the plan was that after the lunar flyby, it was going to be deployed, what they called it, the last bus stop after it had already flown by the moon. You'd do all the deployment and stabilization, detumbling, desaturation, get it all configured so that it was pointing toward the sun, and then start doing commissioning of the scientific payload, checking the downloads, all the things you would do to commission a satellite. And then it would begin its science mission all the time while essentially moving away from Earth. So that you can see, typically by the nominal end of the mission, it would be about 15 million kilometers from Earth. On these, there's a possibility of an extended mission, but the ultimate limit, if you will, on the mission is probably the telemetry link. Again, not a lot of power and not a lot of space. There was a change in plans, and here's one of the drawbacks of CubeSat type missions is that you don't control the launch vehicle. You're riding along with it, and you have to get by with what the primary vehicle provides to you. So after the interim cryogenic propulsion stage has given the boost to the Orion multi-purpose crew vehicle, its primary mission is complete, and consequently, there was not enough budget to analyze the stability of that propulsion system as it traveled on toward the moon. And so they're concerned that because they don't have enough money to do the analysis, the deployer batteries may be too cold to operate much beyond the bus stop 2. And so now CUSP and many of the other CubeSats on the Artemis 1 mission are going to have to deploy earlier than planned. This is going to be a bit of a risk because there is a probability, if you will, that CUSP would strike the moon, depending on the attitude and the drift as it's deployed from the ICPS. So that means that the startup and the stabilization of the platform is going to have to occur very quickly after deployment so that it can use those cold gas thrusters to go into a lunar avoidance maneuver. Otherwise, there's a 29% relatively high chance that it would impact the moon. So all of this just, again, points out some of the risks associated with going on CubeSat-type missions, the notion that you are riding along, you have to take what you can get from the primary launch vehicle, and therefore it's also very useful to have significant design margins to be able to accommodate these changes in the mission and the concept of operations that might be necessary. Another significant thing is the orientation of these CubeSats, because you've got conflicting constraints. As I mentioned, I think earlier, you have to consider the orientation of the spacecraft that's necessary to do a scientific mission. You need to consider the orientation of the solar arrays so that you maintain power, and you also have to consider the orientation of the telemetry link. And those are typically conflicting constraints, which means sometimes you're in a scientific data collection mode, and other times you might be in a battery charging or thermal protection mode, and then other times you may be in a telemetry mode. But this particular diagram here points out the scientific mode, because the purpose of these three instruments is to measure charged particles flowing away from the surface of the sun. And this is some of the science behind it. The magnetic field of the sun essentially develops into what might be called a Parker spiral. So you can imagine this sheet, and the surface of the sheet is where the magnetic field changes from north to south. And these charged particles that are there of interest are flowing along the surface of the sheet. And as they arrive at 1 AU, essentially at the orbit of the Earth, they're coming in at essentially a 45-degree angle. So the instruments have to be oriented such that they're accepting the flow of the particles in, and of course this vacuum helium magnetometer is there to give context to where you are in the magnetic field. So that kind of gives you some insight into sort of the scientific mission portion and how that affects attitude control. Spacecraft bus, very typical or very similar to that spacecraft bus I showed you earlier that was used on the Cygnus mission. And in fact, it was developed by Southwest Research, and this one was explained or described in the 2016 Aerospace Conference. But you can see the block diagram in many ways looks very similar to the bus that was used for Cygnus, just typically smaller, lower weight and power. But one of the things to note, and there's another sort of a diagram showing cusp with the solar panels and the gain antenna deployed. But notice the little asterisks here by these various components of the systems with notation that how many of these are commercial off-the-shelf items. So again, in connection with the growth of this particular segment of the space launch industry, we're getting more and more of the instruments and controls and avionics that are available commercially so that the development costs are lower. Command and data handling system, for example, is provided by Southwest Research. It's what we call our Saturn computer, and it is based on the Centaur design. So it's simply a repackaged and reduced size factor version of the same command and data handling system that was used on the Cygnus mission, reformatted for CubeSat use. And several of the other auxiliary systems are provided by other providers. For example, Applied Space provides the electrical power system with the solar panels, the battery packs, and so forth. The 3-axis attitude determination control systems is a self-contained unit from Blue Canyon Technologies. It's an integrated system with 3 reaction wheels, 2 sensors, sun sensors, a star tracker, and very significant performance capability in a small, lightweight form factor. And then I'd mentioned the cold gas thrusters provided by VACO, 4 cold gas thrusters for direct interface, and again, very small size and very lightweight form factor. The telecommunications are an X-band transponder developed by the Jet Propulsion Laboratory, and this was the transponder that is going to be used for most of the CubeSat missions on the Artemis 1 satellites. And there are several articles that describe this transceiver system in Systems Magazine. So if you want to get more information about communications on these CubeSats, I would refer you to those articles. The CUS programs had several challenges. There's technical challenges associated with the miniaturization of design. There's the challenges associated with the launch delays, the change in operations that I described earlier. And then finally, since this is going to be ultimately a man-rated or human flight-rated type mission, it had much higher levels of safety analysis and reviews than you would normally experience in a scientific mission. In other words, the review processes were much more similar to manned spaceflight program missions. Those all provided quite a bit of challenges to the team. The current status, though, is that the system integration is ongoing. The plans are for delivery of the system to the integrator in February with a launch hopefully sometime later in 2021. Here's a picture of me with the CUS satellite in our laboratory at Southwest Research Institute. In general, the CubeSat engineering challenges, as we mentioned before, are low budget, form factor limitations, size, weight, and power constraints. The immaturity of the technology, we say commercial off the shelf or COTS or not, so there are typically quality issues with these relatively new systems with parts failures and supplier delays, especially with COVID right now, for example. So that requires extensive supplier planning and monitoring, and you have to be very careful about the interface control because, again, it's just simply not quite a completely mature technology base yet. In terms of future directions, there's more and more interest about providing different types of propulsion within the CubeSat constraints, those size, weight, and power constraints, and here's some of the types of propulsion that are being researched. Continued size, weight, and power reduction of both the sensors and the actuators. Better radiation considerations to even further allow longer duration deep space type missions. Improvements in electrical power systems to get higher, lighter weight, more easily deployable solar panels with maybe better high energy to mass ratios, and perhaps even better attitude control optimization so that you can take the very best efficiency from your solar panels and batteries. And then trying to reduce the communication constraints due to the limited available power, the desired data rates, and perhaps some of these can be achieved either, again, through better attitude control or perhaps novel high-gain antenna designs. So that essentially brings me to the conclusion of this particular presentation. I hope that you found it interesting, and I'll just turn it back over to our chair.
Thank you, Dr. Walt, for a very, very wonderful presentation on these small satellites, which are CubeSat, and I'm really happy to see that how these small satellites, they are being used in a very, very deep science missions. So I would like to ask all the participants, if you are having any questions, please type in the Q&A window or in the chat window. We will be taking the questions. But before going to that, Dr. Walt, I would like to know, specifically for the small satellites or CubeSats, and then when they are going to be used for magnetic field measurement, the way it was seen in the cusp, I can see that. How we are ensuring that magnetic cleanliness of this satellite?
Ensure the what of the satellite?
A magnetically clean satellite. How we are ensuring that satellite is not generating themselves, because there are so many components which can generate magnetic field inside the satellite. And when you are measuring, instrument is used for measuring sun's magnetic field. Suppose inherent magnetic field is more than that, how we are ensuring that?
Yeah, it's certainly, of course, the first thing you do is you try to put the sensor as far away from the rest of the satellite as you can, which is why it was on the end of that boom. And then there's techniques for the design and shielding techniques are necessary to take that into consideration. So yeah, you're right. It is a challenge, but it's possible.
So you are going to use some kind of a magnetic shield, new metal and other things for shielding the...
Yeah, to the degree you can, because, it's tricky, because if you add more shielding, you're adding more weight. So every bit of weight you add, that means you have perhaps less power or less performance. So it's very it's a very, very difficult problem.
Okay. One more question I would like to know. When we are going to the smaller and smaller size, there is going to be an inherent EMI problem as well. Electromagnetic interference.
Yes.
How we
Yes.
how they are different from the normal typical satellites, which are having at least some 3 meter by 2 meter by 2 meter volume, whereas in the CubeSat volume itself is 20 centimeter, 30 centimeter, that kind of things are there. So how we are taking care of EMI problems in the smaller satellites?
Very careful design again, and not only that, but in many these instruments I'm describing, they often use relatively high voltages. So, like for example, I know our superthermal ion sensor, being able to handle the difference in charges between the plates, because what you're essentially doing is deflecting charged particles. So that means you've got to put an electric field in this small instrument, and it's an art. I can say it's not totally just design and equations. It's to a certain degree the techniques that go into making these perform becomes quite an art. But it is some of the more difficult aspect of the design.
Okay. And then one more question I would like to take from the audience. There is a question they are asking, why command in S-band and telemetry in X-band?
Okay. I'm not sure that it was. I was looking at that. I was looking to see. I was thinking it is an X-band. I'm not sure that it. I'm trying to look back and see where I said it was an S-band. It is an X-band transponder.
Okay, both are in X-band.
Yeah, both.
Okay.
But they're different rates. They're different data rates. Let me. But they're both in the X-band, uplink and downlink.
Good. So then another question I will take is they are asking, when we are measuring the magnetic strength, then why we can't measure the magnetic strength of the black hole and create the technology to reach into black hole? It will be helpful to study about the black hole.
Yeah, that sounds very interesting, and maybe we will someday.
Okay, so there is a question from Dr. Surendra Pal, who is a very, very senior scientist in ISRO. He was senior scientist in ISRO. Now he is retired and he is AESS fellow as well. And we are very honored to have him here. He is asking, any particular reason to use X-band transponder? I presume you are sending payload data also through this link.
Yes. As I understand it, it's again just that you can get the higher performance that you need from the deeper space missions by using the X-band. They're even exploring possibly using Ku-band in future missions. So I think it was just to be able to get a better performance in the downlink. The downlink seems to be the limitation because they're looking for a transmission rate of 8 kilobits per second. So still, it's fairly slow, but still. It has to do with the improved telemetry information.
Thank you. Then there is again question from a very, very senior scientist from ISRO, Dr. Mahadevan. He is asking, is telemetry part of a payload data?
Yes. There's they do the scientific mission for about let's see, what does it say here? 4 hours. So essentially the downlink is a 4-hour downlink of the data, and then they do an uplink, if you will, of any additional commands for servicing the satellite that are needed after they download the scientific information.
Thank you. Then again, there is an interesting question. They are asking, what kind of material is used for CubeSat? Can 3D printed material sustain the stress in the orbit?
I suspect that it can. I know we've looked at using some 3D printing for some of our sensor components because there's some geometries that would be very difficult to produce with a regular machining type process, and so an additive manufacturing process can give you better, more complex, and lighter weight shapes. So yeah, that is certainly an area that we're doing research on right now. And certainly it might be a good way to be able to reduce the weight of some of those components.
Thank you. And then we are having one more question from our AESS chapter chair, Professor Paddy. He is asking, is electric propulsion an option for attitude control?
Yes, it is. That's one of the areas they're exploring. It is an option.
Yeah. So with this, we are almost done with the questions. Before going to Dr. Paul, I would request Professor Paddy to give a kind of a concluding remark about this presentation, and then I will request Dr. Paul also, because he being the senior most, and in fact he is the father figure in India about space as well as antenna and defense technology. So I would also like to request him to give his concluding remarks. But Professor Paddy, over to you.
All right. It was a very wonderful talk. Thanks, Walt. And we'd like to see you one day physically here. That's our dream someday. Okay.
So,
all right. So the talk. Yeah. You want something? No. All right. So I think this is a very emerging field. I mean, we have also a lot of interest in universities. In fact, in Bangalore itself, there are a couple of universities. There are a couple of IITs working on this kind of missions. Our small satellites have also been launched in some of our ISRO launch vehicles and all that. But most of them are in low Earth orbit. I mean, we never thought that we'll go deep space and all that. But having said that, ISRO has a lot of deep space missions coming up. Maybe some of these things can be taken, and then probably we should explore how do you go forward in that. So that is fantastic. It gave a very nice overview of many different things, power systems, as well as the control system, communication systems. So I think we got a fantastic overview of the mission. And then probably it gives an inspiration for all of us to get involved in these kind of things, which can be doable in academics, in association with ISRO. So thanks again for a wonderful talk. And then I'm sure the audience have enjoyed the talk. Thank you.
Thank you, Professor Paddy. Before giving to Dr. Paul, again, Dr. Walt, I am having one more question because of the way he is summarizing. Another challenge for CUSP are small satellites in the low Earth orbit is charging, spacecraft charging. How we are taking care of charging phenomena for this? Because again, when we are protecting the satellite by putting aluminum shield and other things, again, there is a cost as well as mass impact is there. Are there any unconventional, non-conventional techniques we are using to protect these satellites from mitigating the charging effects?
You mean electrical charge? Is that the type of charging?
Yes, spacecraft charging, when dielectric charging as well as surface charging, I'm talking about those things.
I don't know what technique they use to protect it from charging. I could possibly do some inquiries and respond back, but I don't know the techniques that they use to shed charging.
Okay.
Electrical charge.
So, Paul sir, you are able to hear me? Can you unmute yourself, and then we would like to hear from you about this session, as well as if you want to add anything further.
Maybe we can switch on his video as well.
Okay.
Yes, sir. Please go ahead.
1 minute. Let me see.
Sir, you have to.
Yeah. Is it now audible?
Yes, loud and clear.
Okay. Thanks, Puneet, and other speaker for giving an excellent overview of CubeSat. So, we learned many things, new items that you can have a CubeSat in the flyby orbits. You can take it to the extragalactic regions also. And the new concept which I learned is that he's using X-band transponder in CubeSat, which is a really new thing for me. And also vector helium magnetometer, I heard it. Of course, he's more of it. And I feel that it's a suggestion for Dr. Padi also and others who are listening that it's doable in India also. And Puneet, I think we can suggest it to ISRO. We can do such things in future whenever we launch or Chandrayaan or Mangalyaan or mission to Venus, which I think are, or even Aditya mission is also of that sort, but slightly bigger one. So we are on the right path. Only thing is some of the inputs which he has given, like vector helium magnetometer, using X-band transformer for all these things, we should try to adopt it. And again, I wish to thank you and IEEE Bangalore section and also the learned speaker for a nice input. Thank you very much.
Thank you, Dr. Paul. Thank you very much for joining us and providing your perspective, at least bringing out the Indian perspective on this satellite development. So with this, Dr. Walt, we are really honored to have you and listen you and learn so many new things from you. The way Dr. Paul has told that whether it is X-band transponder or a vector magnetometer. So all those things are truly new technologies as far as India is concerned, and I hope not only ISRO, but even DRDO is also working now on the satellite domain, as well as ISC. Our Professor Padi is the stalwart there. So we will be definitely going to take up some of the technologies which you have discussed, and they are going to be really futuristic as far as deep space science missions are concerned. Because we are very good in communication, navigation, as well as remote sensing point of view, but definitely we are yet to learn so many new technologies as far as deep space science missions are concerned. And I think your lecture has opened a lot of new ideas and questions. In fact, now a topic is really interesting when we are having so many further questions to solve it. So with these words, I would like to thank you very much, Dr. Walt, for joining us, and please accept our digital kind of wishes, virtual wishes for you, and hopefully being 2021 president as well. We expect that things are going to be much better in the second half of the 2021, and we would like to have you in person in Bangalore.
Thank you very much. It's been a great pleasure to be able to present this material because I enjoyed it very much.
Yes, thank you. Thank you very much. So before going to Professor Mazumder, I would like to invite Dr. Manisha to introduce our very, very special guest, Dr. Lakshmi Menon. She is a very senior scientist in Defense Research and Development Organization. So she is going to provide her perspective as far as defense technologies are concerned in India, before taking over a very excellent topic as well as workshop from Professor Mazumder. So, Dr. Manisha, can you please introduce about the speaker and set the context right? Thank you. You have to unmute, Manisha. You have to unmute yourself. No, we are not able to hear you.
You have to unmute.
You have to unmute yourself. Okay, I will try from here.
Yes, yeah, I was about to say that.
Yeah, then. So actually there is some connection problem at workplace. So
no, now we are able to hear you. Now we are able to hear you. Go ahead.
Yeah. So good morning, everyone. I'm Manisha Sanal, scientist from AI group of LRD, and I'm part of SGCOM Bangalore section, IEEE. And I would like to welcome all of you to the event of IEEE for Defense and Space Scientists. I would like to introduce to all of you Dr. Lakshmi Menon, who scientist at and DRDO. And as such, Dr. Menon don't need any introduction in DRDO, but still I'll take this privilege to introduce formally introduce her to all of you. Dr. Menon is a program director of ISTAR program of DRDO. He has made many pioneering contributions to the design, development, testing, and deployment and operation of indigenous airborne early warning and control system, the WNC program, which we some time back was inducted in Air Force. and she has also contributed for various flagship programs of DRDO. She is alumni of IISc, and recently she has been awarded with the Distinguished Alumnus Award from IISc. So I would like to invite Dr. Madam to give a brief description about the event as well as about the work going on in DRDO and in relevant areas. Madam, over to you.
Yes, thank you, Manisha. And firstly, I should compliment the organizers for organizing such an event specifically for defense and space scientists. And as we all know, I will just set a for the next topic on AI, ML, DL, and these are the topics which is the buzzword. And Indian Air Force or the armed forces have also encouraged to pay adequate emphasis on the available disruptive technologies, and that have dual use, and these are driven by commercial entities as well as innovations, and that too to adapt in the context of Indian context as well as specifically in case of Indian defense. So accordingly, DRDO, being the defense research and development giant in India, has also taken numerous initiatives to develop advanced technologies in disruptive technologies. So encountering both state and non-state actors, disruptive technological advancements have potential to revolutionize any nation's warfighting capabilities. And expertise in these areas would provide a relative advantage, competitive advantage in this field. So even though there have been many advancements in several key technologies, which represent significant disruption in contemporary military capabilities, the most significant has been in the area of AI and ML, and that has a capability to give extensive advantage to the soldier and commanders. So these technologies can be deployed in warfare using a combination of surveillance, machine learning, searching, and planning to ultimately analyze big data and automate decision making to aid the commanders in getting an advantage. So through this unique and evolving algorithms, AI can provide a platform for the military which can streamline rapid responses to cyber attacks, conventional onslaughts, and other types of electronic barrages. AI application has been in military use since its incorporation, I understand, from the DART logistics, which was applied for dynamic analysis and replanning tool. So that is the time and battle management in 1991 during Gulf War. So there has been a long gap to actually fully utilize its potential, probably because of non-availability of the hardware that is required to extensively exploit these. And with the advent of and advancements in the hardware, today it has become the buzzword, and even a school children, they are able to talk about AI, ML, and it's everyday word, and it will certainly take in every field into advancement. So India has also followed suit by setting up a multi-stakeholder task force in 2018 to formulate a strategy to enhance the deployment of AI in military functions, and also followed by establishment of Defense and AI Council in 2019. So most talked about applications of AI has been in robotics, and that is to create smarter autonomous unmanned aerial, ground, and underwater vehicles. And the applications in warfare is wide, ranging from reducing the casualties to provide intelligence, surveillance, and reconnaissance collection and analysis for autonomous decision making for time critical targeting. So apart from that, the social benefit also includes generation of new deep fake and disinformation capability. Actually, that can be used during peace and war to weaken the adversary's state machinery to create domestic chaos. I think that's another aspect that is being looked into. So the list is endless, and the government on its part has provided a conducive environment to nurture AI ML technologies through various programs and schemes. And DRDO's CARE, Center for Artificial Intelligence and Robotics, is the pioneer lab leading in the development of AI technologies. And CARE has made extensive contributions in the field of intelligence systems, computer vision, and AI, and has developed comprehensive libraries for image and video processing techniques. Raising the throttle further in this area, DRDO has created 5 defense young scientist labs inaugurated by PM, and one of the lab is dedicated for artificial intelligence with a goal to establish global center of research working in the area of computer vision, speech, forensic, and biometrics with a thrust to dual-use technologies. So DRDO directive also includes creation of and focus on AI by each lab, and under that scheme, CABS has nodal agency for airborne surveillance systems. CABS is Center for Airborne Systems, a lab in DRDO, as a nodal agency for airborne surveillance systems, has initiated several activities in AI/ML for the intelligence surveillance targeting and reconnaissance program and multi-mission maritime aircraft programs, and also to be used in every futuristic programs of DRDO. I also understand LRD has taken up an initiative in the areas of AI in radars for automatic target recognition, and Manisha Sanal, who has been working in this, has worked in these areas of Doppler signature based target classification, AI to improve radar performance, and towards autonomous functioning of radar. So I feel this sets the tone, right tone actually, to announce for the next talk, and by Dr. Uttam Mazumder from Air Force Research Lab on this topic of deep learning for radar automatic target recognition. I think all will be very eager to hear from him. I will not take any further movement on it. I think somebody else will be introducing him. So
yes.
So I hand over, and thank you for this opportunity, and may this field grow further and further for as well as for defense applications and for mankind. Over to you. Thank you. Thank you, sir.
Thank you, Dr. Lakshmi Madam. Thank you for joining us and then providing a very, very insightful information about DRDO, what DRDO is doing, particularly in this field of AI, ML, as well as RCS. And we are really honored to have you, and we hope that as part of IEEE Bangalore section, being IEEE Bangalore section chair, it is my responsibility to invite you as well as your fellow colleagues in CABS and DRDO to be part of IEEE as well as IEEE AESS, so that we can take much more activities with much more vigor, so that all of us can together we can get professionally enriched. And this series is part of that process which we have started and taken up in this year. And Professor Radhakant Padi, being as a chapter chair, he is really working tremendously. So this entire effort is to have a common neutral platform where neither we can say we are from ISRO or DRDO. We all are part of this technical enrichment process, and we should be learning from each other. That should be the motto. And that is possible only when people like you, they are also part of this wonderful organization. And before going towards Professor Uttam Mazumder, I will take few minutes of time to introduce him, because I can see now we are having close to 64 participants. So for them, at least I would like to introduce him. Dr. Uttam K. Mazumder received his PhD in Electrical Engineering from Purdue University, MS in Electrical Engineering from Air Force Institute of Technology, and BS in Computer Science from City College of New York. Dr. Uttam Mazumder is Senior Electronics Engineer at US Air Force Research Laboratory, fondly known as AFRL. His research interest includes in artificial intelligence, machine learning, synthetic aperture radar, SAR algorithms, development for surveillance application, radar waveform design, and high performance computing for SAR-based automatic target recognition. Actually, Manisha was very particular. She wanted to have a talk on SAR-based automatic target recognition. So we could find out somehow that, yes, Professor Mazumder is...
it was my special request.
Yeah. So on her special request, this is being organized. And Professor Mazumder's dissertation research was focused on nearly orthogonal, Doppler-tolerant waveforms and signal processing for multimode radar applications. And he has submitted a patent for this innovation. Dr. Mazumder recently also has published a book on deep learning for radar and communication automatic target recognition. Dr. Mazumder is a senior member of IEEE as well as AESS distinguished lecturer. So I think for this topic, no other person will be better than him. Professor Mazumder, over to you, and we are really honored to have you. I will pass on the presenter's right to you. Please share your screen from your end.
Yeah, sure. Yeah, thank you for this kind introduction. So yeah, it's my pleasure to be here. So let me get my slides. So I think yeah, I work less with the WebEx than the Zoom, so I think I should go to share, right?
Yes. Yes. You have to go to share.
Okay, let me see. I think
Okay, you can go at top. There will be file. You just click on the file, open and share.
Share. Open. Oh, okay, let's see.
Yeah.
That's easy.
Yeah.
Okay, let's see. Okay, that's much better.
If you are finding it difficult, I can share
okay.
my end.
That's okay. I think let's see. Hopefully it's coming.
Yeah, it's coming.
Yeah.
Yes. You can go ahead now.
I can. I saw it's saying still loading, and
Okay.
I don't see the screen.
But we can see.
You can see that? Okay. Let's see. I'm just taking a few more minutes. Yeah. So okay, while it's still loading. So yeah. Again, first of all, thank you for this opportunity to share the state of the art deep learning based automatic target recognition for radio frequency systems. So like as I said, like we are part of the IEEE family, and we are trying to share our knowledge with everybody else. So I gave this talk to another session of IEEE distinguished lecture series, but because you requested me a little longer, and I'm feeling more comfortable to run it a little longer. So so I added like a few extra topics, including my previous talk. So yeah, again, I'll just highlight some of the recent results and technical challenges with deep learning based radar automated target recognition. Let's see, next slide. Yeah, okay. So again, this has been a work that we work together with so many years and so many good people. So I just would like to acknowledge here their contribution. So within AFR, I have a great colleague like Mr. Zalnio. He's one of the greatest person, or considered father of ATR in AFRL. And then I have another person like Dr. John Gorman. So he was a program manager at DARPA, which is Defense Advanced Research Project Agency. So the reason I'm mentioning his name or highlighting him, he was the first person to introduce, deep learning for SAR automatic target recognition. So so that's why I am trying to acknowledge a couple of those guys. But again, I have a rest of the collaborator, and again, I owe them a great amount of gratitude, to work with them. So that's how the work has been done. So here's the outline of the talk. So I'll talk about radio frequency, what it is, and how we do everything on AI ML with radio frequency imagery. Then I'll talk about what is the automatic target recognition. Then I'll talk about recent results on deep learning based ATR. Then I'll focus on the advanced topic on SAR ATR. Then I will talk about how we need to improve the computing platform for, in particular, like if you have energy efficient or like the size, weight, and power constraint computation and future ATR research. So I know that like, we will be running about 3 hours. So please let me know when I should take a break. But otherwise I can continue as long as needed. So here is like the radio frequency applications. As you can see, radio frequency applications goes from the sea level to the surface all the way to the space. So the applications are really endless, and particularly now everybody is putting much more attention to the space. So therefore, lots of applications, more of a space centric. Besides that, like there is nowadays all of the RF or radio frequency devices, like what we know as IoT, Internet of Things. So even though like this talk, we are focusing on radar and synthetic aperture radar and how we can do automatic target recognition. However, another area of radio frequency application is actually signal detection and classification, or also known as radio frequency fingerprinting. So that area is also really evolving. So just to make it clear and concise, so when we say radio frequency applications, so we mean 2 different applications. One is for radar application. In this case, like we take an imagery and we try to classify objects from this imagery. And another area is actually signal detection and classification for device recognition, or RF or radio frequency fingerprinting. So like again, like I'm assuming here, there are also people who are expert in RF area or radio frequency area, but for the sake of to fill in that, okay, well, why you start from RF and what is RF, and so I may cover some of the very basic stuff. So yeah, my apology, like if some of you already know, and so I don't want to give the same the pitch to the choir, like, okay, well, I already know that. So I'm just filling in that, okay, just from some basic stuff at the beginning. So hopefully we can talk more advanced topic at the end. So why do we need a radio frequency? As you know, radio frequency works adverse weather condition like a snow, fog, night, sandstorm, and you name it. So therefore, that's the reason we use radar or radio frequency applications. And so obviously long range remote sensing for ISR, intelligence surveillance, that type of application is also another area for RF or radio frequency. Then self-driving vehicle like car, airplane, and technology, and they also use radio frequency. But interestingly, like this area of self-driving car and things like that, radar has been used, but they use like mostly, I think, point cloud or LiDAR, laser radar. They use more than using synthetic aperture radar. But I feel that synthetic aperture can do, as much than LiDAR. And so I'm not going to much discussion of why they are not using, but like just using SAR or synthetic aperture radar can do, much more, provide much more advantages than LiDAR and optical sensors or visual imagery. So anyway, so that's also another area of application. Then security surveillance, as we mentioned, then multi-sensor object classification. So yeah, we can have combination of electro-optical or video imagery, then infrared, and we can also have obviously SAR And so yeah, multi-sensor object classification also possible. And medical diagnostic. And one interesting area is like a COVID-19 going on right now. So people are using, like a infection detection from chest X-ray. However, I feel that even though this data set, infection detection for X-ray, those data set exist, but usually like for COVID-19 type of cases, like the hard cases, those who has COVID-19 or not, those actually need intervention from the physician. So even though chest X-ray sometimes used, like, whether someone really has the COVID or not, but I think, still, like, I think people try to apply machine learning for chest X-ray for type of infection detection. So yeah, here is an example of a video imagery and how it looks like into the synthetic aperture radar imagery. So as you can see, the image on the top is a 10 classes of military vehicle, and which is like optical imagery, and the image below is actually the radar or SAR, synthetic aperture radar imagery of these objects. So as you can see, just considering, like, we can apply deep learning or machine learning to the radar imagery to recognize those objects from SAR, it was like a really big step. So actually it started back in 2013 when like the DARPA, Defense Advanced Research Project Agency, they thought that, okay, well, we have to think of doing ATR from radar different way. So we used to do template matching in the past. So how we can apply modern driven machine learning to classify these objects from SAR or synthetic aperture radar imagery. So again, like as you can see, like around 2012 or 2013, like that time machine learning or deep learning was applied to the ImageNet and other type of data set, which are like visual imagery, like the pictures of the military vehicle you see on top. So at that time, consideration for deep learning to apply to the image to the bottom was really unheard of, so but like the DARPA did a seedling effort and see that, okay, if we can apply machine learning for correct a number, like a recognition, like MNIST, like a handwritten digit recognition, 1, 0, 1, 2, 3, 4 up to 9 recognition. So why can't we apply those techniques for military vehicle recognition? So there has been a small study to show the promise, and then sure enough, so things actually worked out. So that's how the deep learning based SAR ATR began. And so there has been a big program after that in around 2014 to do further investigation of applying deep learning for SAR ATR. So again, like a real summary for this slide is like those who are not a radar expert or those who have not seen radar imagery a lot. So just to give you a visual cue of how the radar imagery look like versus like a visual imagery, and how machine learning can detect and classify military vehicle from SAR imagery. So this is like the end of this slide. So now on this slide, you can see how the image look like a SAR or polarimetric SAR, how this image look like. So here you can see that this is like a full aspect, a 3D target reconstruction of using interferometric circular SAR. So, the key message from here is that even though in radar imagery we see lots of speckles and dots, and it doesn't make sense, but if we incorporate multiple polarization, or if you would like to construct 3D image from SAR, it is possible. And so in this case, you can see how a military vehicle looks like from SAR imagery. So even though traditionally we see visual imagery, colorful imagery, not much to the SAR, but it is possible to make a SAR imagery or interferometric SAR imagery that looks like really in 3D. And more importantly, if we use multiple polarization, let's say HHVV or cross-pole polarization, you actually can encode those information like RGB, color imagery, and then you actually can make a color imagery from SAR. So here is I was talking that how the object looked like in various spectrum. So as you can see, if it's say in a tank, and I'll tell you, just focus on the left, top left signature, like K band SAR with HH polarization and K band SAR with a VV polarization. So as you can see, K band SAR and K band SAR with the two different polarizations, their signature is really different. And in particular, you can see here the dots that represent barrel, it did not show up much to HH polarization. It shows much better, but in VV you'll see. So the conclusion here is, when you talk about SAR imagery, polarization actually bring you additional information. So even though traditionally, when we make a radar system, a SAR system, so single polarization is in most often used. So however, this image shows that if you really want to get more information, multiple polarization could bring you more information. And so here also you can see other type of signature across the spectrum. So radio frequency data. So now we are going to the main area that why we are not doing machine learning or artificial intelligence, machine learning or deep learning, you name it. Why we are not doing more and more of machine learning on radar imagery. So the real issue is that unlike video imagery, radio frequency data are really difficult to collect, and mostly because getting a measured radio frequency data or SAR data involves radar sensors integration and data collection by certified aircraft. So these are you have to reconfigure the radar system, and in particularly I'm not sure how it works in everywhere, but here to do those things in the USA, you have to get the certification and so much of the things going on, and detailed experiment design and ground truthing. So in particular, any of this data collection really cost $1 million in USA. So it's not like that video imagery. You just go outside and take some pictures and you get the data. But radar imagery is not actually possible, to get those things in a really inexpensive way. So therefore, measured SAR data or radar data are actually expensive, and you don't get them freely available as you wish. So yeah, here is a little bit of about a measured radio frequency signature. Now for machine learning application, we can think of how we can use the SAR signature or SAR imagery. So we call one-dimensional SAR as a range profile. So basically, we get the pulses or error return, and you do an FFT, and you get like an 1D SAR or range profile. So it basically shows a blip of presence of the target. So those range profile are also known as also HRR, high range resolution. So and previously or like a long time ago, those things have been used a lot. HRR or high range resolution signature or one-dimensional range profile has been used for radar object recognition. However, nowadays we do two-dimensional SAR, which is actually an image of a scene or a target. So in general, like if you would like to make an image of a radar object, so an object using radar sensors, so we typically would like to have 1 foot resolution SAR image, and which actually in X band we need about half a gigahertz bandwidth. So that's kind of rule used how you make a radar system for radar for a SAR image. So like as I say, like detecting and identifying object from radar could be hard for human operators. So like again, image to the left and image to the right, like a visual versus SAR. So from left visual imagery, anybody can see it and say that, oh yeah, it's a tank. And from the right image to the right, it will be really impossible for people to see in open eye and say, oh yeah, it's a tank or something like that. So again, like the message here is that radar imagery is not really very visual to see. Other than the image analyst, they can see what type of target it is, but it's not possible for traditional human that it's a radar image or not. Then next slide. So like a kind of gave a segue for what we can do if we don't have enough radar data, measured radar data, because it's expensive. So another way to get radar data is called synthetic radio frequency data. So the synthetic radio frequency data is could be generated by radar simulation. So we can use electromagnetic prediction code to generate like a radar signature. So this is like an inexpensive way of getting radar data. However, to do this, we need to have a high performance computing, because of all the calculation goes on, like Maxwell's equations, those things behind the scene, really very expensive. So yeah, you can have electromagnetic prediction code, and you can have a model of an object, then you can actually generate signature. But like as I said, like with high performance computing, it may also take sometimes days, depending on what type of fidelity you want of your signature or that of a particular object. And also it depends on what type of frequency band you use, and also how many targets on the scene, do you include the background clutter or not. So all of those things kind of matter depending on how good signature or how accurate signature you'd like to predict. So to summarize, it is possible to generate synthetic radar data in an inexpensive way. However, we have different types of skills or different types of method, like electromagnetic prediction code and supercomputer, and all of those issues need to be accounted, and then you can get signature radar signature in a synthetic way. So for as our focus is on how we can apply machine learning or deep learning for SAR ATR. So the biggest thing we need for this type of application is data. So AI, ML, you name it, and so the most important thing is data. So in general, if you go to the industry like Google, Facebook, and whoever developed the deep neural network model, they'll give you the software for free. However, they will not give the data for free. So that's actually one of the things that what's going on with machine learning in open world. So in particular, with radar data is not much available. So, but thankfully, AFRL here, we actually public release quite a good amount of data set available for research for the community, so that the machine learning algorithm could be better. So with that, here are list of data set that you can use, and these are available to get for machine learning research. So the first data set is called MSTAR data set. So again, the link is provided. And so the MSTAR is a DARPA program back in 1998. So they use this, they actually collected the data set for ATR algorithm development. And so again, you can go to that link and you can have this data for machine learning research. So now, if you can see SAR literature, any SAR ATR, perhaps 90% of the papers are actually, you'll find that they refer to the MSTAR data set. So that's really easy data set to get and play with the SAR ATR algorithm experimentation. And the second one, AFRL public release to us called sample data set. So that's also another one, and I'll talk more about this data set later. Then another one AFRL published was called PAMS data set, and they didn't provided the link yet, but I think they'll be provided soon. Then another data set is called civilian vehicle data set. So that's also a data set available for civilian vehicle classification. So going back to sample data set, again, I'll talk more about that. So that was created to study something called transfer learning. And again, I'll talk a little more later. Then recently, interestingly, we found a data set from China. They actually released or they make this data set available called ship detection data set, and it's in GitHub. You can get there. So they basically released this data set for the problem of detecting ship. So again, it's quite interesting. The China, they're giving away data for free. So these are also satellite imagery. So one bit of caution is that there are so many things going on with machine learning or deep learning. So sometimes people give you data set, and these data sets could be poisoned, or in a way, as somebody mentioned, a deep fake, or making people fool, or making propaganda. Meaning that in this case, we don't know, or we have not been investigated the ship detection data set from China, whether they made any poisoning this data set, so that they may think that, okay, well, those who are using this data set will develop the model for classification, and then if somehow we apply to the other data set, this may not work. So yeah, you have to take a bit of caution, whether this data set is real or not. Then another one, number 6, is called RF signals data set. So as I mentioned at the beginning, there are two different types of RF application. One is SAR imagery, and we do automated target recognition for object recognition. And however, another application is signal classification, or RF fingerprinting. So the RF signal dataset from Northeastern University is actually being used for RF or radio frequency fingerprinting of devices. So basically, if you have Wi-Fi or other type of devices, you can really use this dataset to detect and classify an object or device based on their signal. So this is like a handful of dataset available right now for machine learning based SAR or radar ATR development. So let's see the next slide. So again, like the M-STAR dataset, and a little more detail. So the M-STAR stands for Moving and Stationary Target Acquisition and Recognition. So this program actually was a DARPA program back in 97, 98 time frame. So as you can see, this, like as I mentioned, this data is the most used data set, and the published version of this data set has 10 targets, and you have a 2 degrees, 15 degree, and 17 degree elevation angle. And so these are there are a number of imagery available per degree. So yeah, you can use this data set for automated target recognition study. So the next data set, the sample data set. So the sample mean synthetic and measured paired leveled experiment data. So again, like here, these are also military vehicle, and so the goal for sample was that if you have let's say we don't have so much of measured data, but we have only synthetic data. So now how we can develop like a transfer learning or domain adaptation algorithm so that we can possibly train on synthetic and test on the measured and see what's the performance. Or you may have small amount of measured data, but you can have a lot more of synthetic data. So you may use a combination of synthetic and measured data for training, and once you train the neural network, then you can test with the measured data. So again, like the elevation angle for this data set was 14 to 17 degree, and again, these are all 1 star expanded single polarization data set. So there is a paper associated with this data set as I listed. So they basically published this data set and also associated challenge problem, what can be done with this data set. So like as I said, sample data set has been publicly released for transfer learning research based on those M-STAR data set. But there are some difficulty this generation of this type of problem data set. Basically, they try to make sure that, okay, well, when you generate measured data, so you know what elevation and azimuth angle this data has been collected. So when you pair measured data with synthetic, so the synthetic data or electromagnetic prediction code, it also has to have the same type of articulation of the target and same type of orientation or collection geometry. So they really work hard to make sure that both the paired data, like synthetic and measured, they resembles, and so that we should get expected results based on that. So this is like the sample data set. Okay, so next is PAMS. So let's say so this is also an extension to the you can say the sample data set. So it's a performance estimation for multi-sensors ATR data. So the goal for this data set is that that, to further experiment the capability of automatic target recognition. So one of the biggest issue that people say that, okay, well, I develop a machine learning based automated target recognition. So yes, I am getting 95% accuracy or 98% accuracy, but those kind of saying or statements are totally useless unless it has been saying in a context. So what it means that, okay, have you tested your algorithm or evaluated your ATR on extended operating conditions? So extended operating conditions meaning that, okay, you get 95% accuracy when a tank has a barrel. But what about, if you do not have the barrel, do you get the same type of performance? Or what about if you vary the elevation and azimuth angle geometry, do you get the same type of performance? What about if you change the radar frequency band? So the list goes on and on. So technically, if you develop a better automated target recognition algorithm, it has to be really very comprehensive evaluation, so that you know what kind of performance you are getting and why you are getting bad performance. So we have to know those things ahead before you make the decision that this is the target you are looking for. So here, like the targets has been data has been developed. Let's say BMP2. So one version has no mount assembly, and M2NA it's a target that it has no missile launcher assembly, and like T72 has one version has a barrel, another version do not have a barrel. Then Zoo 234, a version has no radar assembly and another one has radar assembly. So basically, within like an object category, you can vary its orientation or give less information and see how ATR perform. If you take away some of its assembly. So the PEMS data was like more of a performance evaluation of ATR with extended operating condition. So again, like there was a talk about this data set, and you can see the paper at a SPIE. So the next data set is called civilian vehicle data set, so CVDOM. So yeah, okay, I'm going back to the previous slide, the PEMS ATR data. So again, like this data also synthetic, meaning that this data has been generated with electromagnetic prediction code as from simulation. So as you can see, if you have those electromagnetic prediction code, you have more freedom of generating like a target signature. And same thing if you would like to go in an open field, collect data collection by radar. So as you can see, you just cannot, collect radar data like, a tank with barrel or without barrel, right away. So, however, like if you think of generating data synthetically, and you have much more freedom to get those signature as quickly as possible. So yeah, the civilian vehicle data dome. So again, like here, like these are all civilian vehicle object, like 10 different class. So these are like X-band data set data, and so these are like used for civilian vehicle classification. So basically, you can mix and match, like if you can add this type of targets with military vehicles, then you can see how ATR performs distributed between civilian vehicle versus like military vehicle. So this data, there is a data set that has been publicly released that we can use this data for SAR ATR as well. And yeah, here is the radio frequency shift detection data set from China. So yeah, they publish a paper, and also they put this data set into GitHub. So yeah, you can use this data for maritime object detection. And again, these imagery are actually satellite Chinese Gaofeng, and they also possibly put some Sentinel SAR imagery as well. So yeah, you may look into this data set as well. So having said that, I kind of covered, what type of data set available. So again, before going into much detail, so we need to have really good amount of data, for machine learning. So as more data we have, much better for ATR or machine learning algorithm to perform. So next couple of slides, I'll just briefly tell the AI ML DL. So many of you already know. So basically, like who is who in this field. So we in radio frequency applications, we kind of borrowing what has been developed to the commercial world. So like in that world, like Jeffrey Hinton, he's like, and also Jeffrey Hinton from he's from Google, and also he's a professor at University of Toronto, and then Ian LeCun from NYU, and then Yoshua Bengio. So they're like the godfathers of AI and deep learning. So like when people think of, okay, what is AI? So AI is like more of machines to think or behave and react. And machine learning is like a data-driven learning algorithm, and deep learning is like more of a brain-inspired neural network for classification. So in a nutshell, like you can think of artificial intelligence is a superset, and then machine learning is a subset of artificial intelligence, and deep learning is a subset of machine learning. So yeah, so those definitions, like you can go much more deeper. So, but those are like the things going on. So yeah, so when you hear the buzzword AI, ML, DL, so what are those? So again, like artificial intelligence is more of a big umbrella of everything that a machine or autonomous system can do, and machine learning is like like a subset of artificial intelligence, and the deep learning is again another subset of machine learning. So that's how we kind of see the relationship between AI, ML, and DL. So like one thing to say that in a DARPA, like there has been a nomenclature, like, okay, well, where we are in terms of artificial intelligence and machine learning, deep learning world. So DARPA categorized like the artificial intelligence as waves, like the first wave, second wave, and third wave. So the first wave is kind of like describing something like handcrafted method, and then second wave is like a more of a categorized like what we do with today's machine learning is like more of a second wave, and the third wave is like which now we are trying to go more of a reinforcement learning and more of explainability, how something works. So those are like the three waves of AI development going on. So again, like nowadays we are trying to make machines more and more autonomous, and kind of what is called reinforcement learning. So we may initiate machine to do something initially, but the rest of the work, machine should sense the environment and then tell us, what's going on. So within this machine learning algorithms, like, they're like, what are those? So like, again, next few slides, I'm just giving like the little bit of overview of what's going on with AI and ML. So when people see machine learning, it's like, oh, so someone may say, okay, well, yeah, I did machine learning. Yeah, I know support vector machine. What is this? Oh, I did a neural network. What is this? So I try to categorize based on what are the machine learning categories in broad. So with that regard, we can see machine learning as like supervised, unsupervised, and semi-supervised, and then transfer learning, reinforcement learning, and nowadays there is a generative adversarial network or learning. So the next slide kind of shows the more of a category, like how it works. So like supervised learning, we have a linear classifier, non-linear classifier, and within this linear classifier we have perceptron, support vector machine, passive aggressive, and linear regression. And so within non-linear we have neural networks, kernel perceptron, and k-nearest neighbor, boosting. So even though the mainstream of machine learnings are focused on more of deep learning, but like all of those other things has been used a lot, like nearest neighbor, boosting, those has been used. So within neural networks there is feed forward neural network, recurrent neural network, stochastic neural network. So as you can see, we can further categorize forward neural network as convolutional neural network, multi-layer perceptron. So again, these things has been evolved. You may say, okay, well, what is the convolutional neural network versus deep neural network? So again, they're pretty much same, but there is subtle differences, but they're not like a huge difference. But I will talk more later. Then within recurrent neural network, there is a long short-term memory or LSTM, and there is a probabilistic convolutional neural network. So again, you can go deeper. So the main point here is that I try to make sure that those who are first to the machine learning, and they can see the big picture. So this slide kind of capture what is machine learning all about. So now the unsupervised learning, so the K-clustering, K-medoid, and Gaussian mixture models, those are also been popular. And again, this algorithm still has a value for some of the machine learning applications. And semi-supervised learning, like the way we mentioned, we may have some synthetic data and some measured data for training. So okay, I think I saw maybe a question. You say RNN and HMM have some difference. So again, like a recurrent neural network and hidden Markov model. So there could be like a subtle, difference, but some people may say yes, and some people may say not. So again, sometimes people see in a different way. But again, hidden Markov model, well, you can think of feed forward and neural networks. So again, you go back to the previous layer or of information and go back. So RNN, like a recurrent neural network, yeah. So in some way they are same, if you think that way. So but the main point here, I'm trying to capture is that so the machine learning algorithms are so different, and then sometimes we change a little bit, say for example passive aggressive versus SBM, so or the just perceptron. So they have been evolved on one way or other a little bit, then give a different name. So yeah, so the recurrent neural network, and hidden Markov model. So the recurrent neural network, you go back to the time, and then you find sequence or things like that. So those also has the same reason in a hidden Markov model to use sequence finding. So yeah, they have some similarity with that regard. So yeah, so again, transfer learning and reinforcement learning, again, also another kind of new branches, or so to speak, now evolving as their importance getting. So, so the last slide here, yeah, 3 waves of artificial intelligence, like we mentioned. Like the first wave is more handcrafted. The second wave is more machine learning, systems learn of statistical model of specific problems using big data. And the third wave, contextual adaptation. So the more and more is like, human-machine interactions, how we can get better results. So one thing to mention here that people say that, okay, well, like there are 2 sides or 2 groups you can see. Some people say, okay, well, should we rely on machine for complete autonomous, like, they should make that decision themselves, versus should we, should the human should be in the loop. So which is like, human machine intervention or interaction. So like, for example, like Google, they like to have everything should be done by the machine. And so basically it says that, okay, well, we want machine to be as close to the human brain. But I think we are far away from that, and that a machine should be complete 100% autonomous. But people think that if machine with a human in the loop, we are always safe and we are better off with that regard. An example, people say that, okay, let's say if you play a chess, they found that, okay, well, yes, you can develop a chess game, compared, with artificial intelligence, everything you put together. But they found that, as much time or as much capability a machine can have, but if human in the loop, they can be, but they could be a stronger team for solving problem than just machine itself. So there are 2 groups of people, or you can say that scientific community, who are in favor that, okay, machine should be completely autonomous, or other people say that, okay, well, forget about that. We don't need that. Why not human could be at least to some extent in the loop, and we will be always be better off in case machine make a mistake. So yeah, next slide, I'm just go quickly a few things that because we are user of what commercial world is developing for deep neural network architecture and software. So how all of those things detail inside, I think we are kind of using what they have, the commercial world has developed. So having said that, if you would like to do any type of experiment of your deep learning based automated target recognition, so like a LeanNet, AlexNet, and BGG, and GoogleNet, and ResNet, these are like the top the DNN, deep neural network architectures available. And like as I said, like I'm more of a radar, and we are applying machine learning for radar problem. So if someone would like to know all the details and nitty-gritty, I would suggest to go to the Stanford University lectures available to YouTube. And so those are like really phenomenal videos, and they possibly describe more than for us or for even me to describe all of those things and nitty-gritty details. So I really highly recommend to go to those lectures to know all of the details of how these things has been implemented. Now the software tools or hardware used for machine learning. So again, Python and PyTorch are nowadays are very common. PyTorch are the most useful software people are using nowadays. Then also Amazon Web Service, AWS, also have some of those well, it's being AWS or Google Colab. You can use Google Colab. You can get some free GPU for training. And AWS, yeah, you can use them, but you have to pay. And obviously, like there is NVIDIA GPUs also available. for training of the deep neural network model. So the thing is, Amazon and Google Colab. If you think that, so nowadays, you hear the word like the cloud computing or distributed computing. So this kind of AWS or others kind of gives you an edge that you can have your data on web, so that you may have researcher working on one place or other, but anybody can have access to the data in a centralized server, and anybody can have access to this data set. So these are also recently, AWS and others are also becoming kind of business area, or like even if your organization, like your organization want that work with people collaborate themselves. So many organizations, like they try to collaborate themselves using like more of a cloud-based computing platform as well. So that's what I think Amazon is getting into this business as well. So let's see. So these are like the tools. So again, like quickly, like how this deep neural network models work. Like you have input layer, then hidden layer, and the output. So you have an image or object which is represented as a vector, and then we try to match with the model that train imagery, and to the level we try to match it, and then try to optimize that how the train model looks like the real object. So like as I said, like I'm just putting those slides here just for visual to see that how these things works. But like I'll refer to the Stanford video for more details of knowing how these things works. So like I'm kind of coming end of the basic overview. So now many of those things I'm talking here. So we have a book actually on deep learning for radar and communications, ATR. So like this book has everything. So when I started with Air Force Research Lab back in 2013, so 2003 actually. So that has been in great need for an radio frequency ATR. So, but people tried, and then it's a very tedious thing. So, but fortunately, like me and two of my other colleagues, we were able to get it done. So many of those algorithms we discussed here could be found in this book, as for more details. So again, like there is a reference of more details of what I talked today in this book. So so now what is automatic target recognition? So like again, like we say ATR is not just okay, this is a car or an object, but it has a really a big glossary of terms, terminology, like what is detection, classification, recognition, identification. So and what we do with it, and so there are like a few handful of definitions. So I try to put it here, but you can get more about it on the paper I referenced here. So the SAR ATR approaches. So how it was done. So previously it was done like mostly template matching and model-based vision. So basically. The M-star data set that I mentioned early, that that program started using a template matching approach. So the template based approach, is basically you have an object and take an imagery or screenshot from all different azimuth and elevation angles, and then you put into the database, So once you go to the real,
Mazumder, 1 second, Dr. Mazumder. I think slide is not navigating. So which slide you are showing right now?
Sorry. Yeah. Slide number 26. Yeah. Yeah. So I had another screen. So yeah. Sorry. Thanks for the reminder. Yeah. Yeah. So yeah. So yeah. Thank you. So so the ATR, like, it has a good amount of terminology. So I just put there for reference, like what those terminology means. So the ATR approach that we have, template matching that I was talking about, like we have, you can have millions of signature of a particular object, and then we try to match with a particular day of collections, and whether it's match one of those million imagery. So as you can see, like the template matching, yes, you may get good results like by matching, but it has so many disadvantages. Namely, you have to have millions of signature of a target from all different azimuth and elevation angle. And then you have to maintain a huge database of signature. Then also computational cost, and for us the biggest our biggest issue is that it's like a template is like a more of a memorization of signatures, which is like, in a sense, that if you have a little bit of variability of the target, you may not get the good accuracy. Your accuracy really drops significantly. So that's not a good approach. Then another approach they tried was called model-based approach. So yes, in model-based vision or model-based approach, here, like you can make a more of a 3D model of an object, and then that will be more robust. However, like that also come to the same ballpark of computationally expensive, and it's not easy to insert a new target signature as easily, but it gives you much better results than template matching. So so now here is like a more of a template-based matching approach. So basically, if you have an image X and Y, and you have a template T of X and Y, so the goal here is like we have a large image with so many targets, and I'm matching with one particular target. So as you can see, it goes by block by block searching pixel by pixel. So it's like a really computational, like tedious. You don't want it to be running in real time. So like the data processing, storage, and collection, and the time it takes for computation is really humongous. But still, like there are still systems that still uses template-based approach. But like as we are doing more and more deep learning-based approach, so these things may not stay. So the more details of this, method could be found to the paper referenced here. Now here is like like giving you more concrete example of what's the problem with the template-based approach. So like here you can see that I have P72 1 dash star and 1, 2, and 3, and so the 1 dash star means that I have used this version or little bit of variations of target for training. As you can see, that your accuracy is really good, like 95% or more, 95 or 96%. But with a little bit of slight variations, you can see the performance drop to 57% or even 67, 69%. So what it says that, okay, if you have little bit of variability of the target that you did not train, and you can see that performance really kind of tanked, it's not really good at all. So those are like the biggest issue for template-based approach. So again, like more details you can find the paper referenced here. So like with the new approach with the DARPA Trace program, trace is a target recognition and an adaptation for untested environments. So sure enough, like, with MSTAR data set, an initial experiment actually shows about 99% or even more accuracy using this approach. So and also they're really good in target variations. They actually perform really good. So so further, like, in deep learning based approach, you can develop your model as a complex deep neural network like I and Q, two different channels. So you can make an actually complex neural network model as well if you want. So but the bottom line is the stark difference between template based approach versus deep neural network is a huge, and you don't want to go back to the template based approach if you use the deep learning method. So now next couple of slides, I'll emphasize of how to make effective ATR. And here, like, the main point is that if you really would like to do good ATR, and you are really confident, you have to follow some rule, or like, as a systematic way. So now, as you can see, with deep learning or machine learning or anything military-based military applications of AI, one of the biggest issues, okay, you will see that people will say, what's the ethics? Should we use the AI, ML, or deep learning for military applications? Meaning that what will happen, like, if you made a mistake that you think that it's a possible target, and then it found out to be a school bus, and so what will happen? So that's why, like, ATR development should be very rigorous. That what you're doing, be very, very systematic way of doing. And part of the things, like, I can share a story so that Professor Hinton, like one of the father of the AI and ML. So he's from Canada. So they are against all types of war and any of things, and for whatever the reason. So, and in their mind, they think that, okay, well, for military application of AI and ML, could be that, okay, well, you make a system and then take it to the war zone, and you just kill people based on what you see, that, oh yeah, this guy is a bad guy without knowing it. So, but like I say, like, so those are like the issues coming in, like the military uses of AI ML is very some people are really, really concerned that, okay, well, yeah, we may accidentally kill so many people, but actually, but they don't know that, like, to do that, there are some rules in a way that, that is AI ML and that Facebook and everybody use. But like, as I said, they use very pristine imagery, and so their results are really, really accurate, and also in a way there is a terminology for those type of AI and ML, and these are called like a shallow AI. Shallow meaning that those type of applications have so much data, so these are like almost always accurate. They don't do rigorous ATR like the evaluation. They don't need, because they have so much data, and their accuracy is really good, no matter what. However, like as I said, like for military application, this is not the case. Another example of, like, recommender system, like if you buy or sell something from Amazon or any of those online based or recommender system, they will tell you, oh, you like this, you may like this as well. So those things, like, they have so much information about some of those this type of problem that they are always good in terms of making the recommendation. So their evaluation don't need to be as rigorous, like, as for military application. But for military applications, like, we don't have tons of data. We lack all of those data. So therefore, we have to be really careful how we use those data. So now what I have talked here, I think, those academic researchers, they don't know that, we follow some guideline and we try to be as accurate based on the decisions. So it's not that you just go somewhere, you think that is the target, and let's say make an action on that. So it has
Dr. Mazumder, we are having few questions. Would you like to answer those?
Sure.
Yeah. So what is the approximate time for ATR on typical SAR using trained models?
Like I said, for training, what is the typical time for training?
Yeah, I will repeat. What is the approximate time for ATR on typical SAR using trained models?
So like I will try to break it in two parts, like the training, the model, and then after you make the trained model. So first of all, like the training, the model, it could be taking days. It depends on data, or it may be taking even less time depending on how fast computer you use for training. So training, developing a training model is the first part, and it may take couple of hours or days based on how much data you have and how fast computer it is. So therefore, the trained model development is the first part, right? And then second part is that once you have a trained model, then we call it inference engine. So now you go to the field and you have the imagery coming in, and you are inferencing based on your trained model. You already have a trained model. How much time it takes? So once you have a trained model, testing or actual classification could be taking seconds. And it depends again how fast computing device you have. So it depends on your applications, and also on whether you are searching, if you have 50 different targets and now you are trying to classify each of them, that's a different problem than if you think that you have only 5 or 10 particular objects and your goal is finding the one you're looking for. So the two parts, one is the actual training, how much time it will take. It depends on the data and your compute powers. It may take a couple of hours, 2 days. Then once you have the trained model, doing the actual classification could be done within seconds or minutes. Again, it depends on how many targets you would like to classify. Is this did I answer your question? So yeah,
Lakshmi, madam, you wanted to have
question.
Yes, please go ahead.
I have another one question. Yes, actually, if that model template you're telling, and in addition to that, another approach you're telling that whatever behavioral model based. So if combination will do better, no?
Combination will do better. Yeah.
Yeah, equivalent to that, if I'm matching template and with this different aspects are there. So that is behaving like my behavioral model, right? See, template matching is like same thing again and again. And if aspect angle are changing, so aspect angle change means I'm modeling the behavior, right?
Yeah.
So if put together, I'm training my thing with different aspect angles. So I use CNN instead of RNN. That will do only computationally. Okay, there will be difference, but that will be the ultimate solution, no?
Yeah. So I think that the biggest issue is that, as you can see, the So the template and model-based approach, if you combine those two together, the real issue is like the statistical, like a deep neural network model. It has capability that is not really fully memorizing the target. So like, if in real applications, if you think that target, like, in this case, like a tank may have a barrel or may not have a barrel, or like someone could change the, let's say you have a T-72 tank, now it has changed 20% new features than before. So the real question is, either your template or other approach, it can get the salient features. Like, let's say, for example, if you would like to know me, or like you'd like to memorize my how I look like, you don't need to see everything about me. You don't, or any object. You don't need to see. You just keep the this person. I saw that this person has the eyes are kind of gray, or something like special feature that you'd like to consider as the most important feature. So the difference between a deep neural network model is that, like, it's kind of able to find the key features very fast, or we call it salient features. So that's actually kind of going away a little bit of that. Okay, template-based approach is like a more of a memorization. I told you these are the things you should find, and therefore you kind of make correlation and you give me good results. So that's the biggest benefit, of the deep neural network model. So yeah, you'll see
that is what means. Somewhere or other, when we are finding that kind of features, like you're telling eyes are existing or not, that is also means out of that bigger template, I'm finding coming down to a template. Rest I have discarded. Rest of the features I have discarded. Only that particular few features I'm retaining. It's but that is also kind of template matching.
Yeah, it is also.
So basically, that.
Yes, it is. So
because I think then that HAR wavelet or that this thing.
Yeah. So actually, like I
have that pooling means that layer, that convolution layer. That will help me to get those particular features, no?
Yeah, exactly. So you can kind of you can massage like within this convolution layer. What are the key features you would like to do? You can do that. Those kinds of kind of handcrafted or like hand selected some features. You can do that. So maybe as the talks goes on, there will be like examples, like you can see that where are those things came out, and then you can see. But like we're kind of convinced that template based approach, the issue is like if you don't get good results, you have to have so many of the templates, as many of the templates, as much matching. So which is like you have to maintain a database, and then you do the correlation, so much. But I think if you like to have near real time or real time performance, and deep learning is kind of give you the fastest kind of solution. So yeah, I think again, like I'm still like a way behind. So maybe I'll go real fast, then go to the actual problems that you'll see that how the deep learning kind of helps a lot. So yeah, so again, like I bring that issue of like the ATR development. So in a way that many countries are concerned that either to utilize machine learning for this application. So so that's why I think we are very careful. So like let me go fast on this. So the confidence, like you have to be confident that okay, well, your model is really give you good. Like in this example, if you think that template and other gives you good results and your operational need, and you are getting consistent results, you may be better off with those approaches as well. Then understandable, how does it work? So like again, one of the biggest thing about deep learning is it's considered to be a black box. So the explainability of the deep learning is really we don't know all the things. But another way of saying is like a deep learning is not a closed form solution. Like we don't it's not a like 100% physics that we expect that to happen. So therefore we always should expect a yes or no questions. So there is like something about it's a black box in nature, so that bothers some people. But initial layers, you can see that when it selects the features of a particular object, it goes by detecting the line and then putting the line together and getting a kind of line, triangle, and other things. So it kind of gets to the features. So,
what I understand that way. So is it like multiple that convolution layers, whatever result comes out of it, fusion of that, and that is taken as fusion of that data, and that is taken as feature?
Yeah. So that's
multiple layers, convolution layers we are saying.
Yeah.
And
so
fusion of those multiple different convolutions. Some may be detecting edge, some may be detecting particular color or hue or whatever, and like we are fusing it together, sensing data fusion kind of, and then that can be. Yeah, so I think that is how it works. No explainability, I feel.
Yeah, so that's exactly right. So but like as I said, like some people has difficulty to accept those reasoning that okay, it's going step by step process, and you actually can see that what are the salient features like at the end, like when you fuse it goes. But like so some people are not really keen to accept those reasoning. So next slide, the robust, like how do you gracefully degrade under variability, and out of library like confusers. So let's say out of library distribution or confuser. So this is very, very important. So like as I said, you have two different targets and they could be very similar, or they could be, one guy could be confuser and another will be the real one. So how ATR kind of able to discriminate two different kind of objects. So those are very, very important, that how good your model. Then performance modeling, like with targets of variability, different environment, and sensors. So basically, like if you consider environment, if it is a cloudy environment, how the background look like, and they also influence the decision making. The sensors type, rarer sensors parameters like frequency band, and they may increase your resolution or decrease. So how those things varies. So that has to be understood. Then training with synthetic data, 100% synthetic data. So how ATR perform with the synthetic data, those things has to be studied. Then real-time training. So again, yes, if it takes a couple of days for training, that may not be good. So and particularly, let's say you have a database of targets. If you expect to get a new target, how the training will take time. Is there an incremental training possible? And so those things has to be also take into consideration. And perhaps like there are metrics of evaluation. So you have to see how your ATR perform with different types of metrics. So now I'll just go quickly how the single target classification works and multiple target classification works. So the single target in this case, like we kind of consider for civilian vehicle classification dataset or CVDOM dataset. So like when I mentioned like the electromagnetic prediction code, so there is a code in the paper describes called with a simulator X-band scattering data has been used here. This data could be fully polarized, but I think they distributed data only one polarization. So again, these are like the classes of target, and using like the electromagnetic prediction code, you actually can generate the synthetic data with a full azimuth and elevation. So one of the biggest issue, unlike the video imagery, is that for radar data, we collect the data, then you have to form an image to make those imagery available for ATR. So the real issue here is that there are different imaging schemes as well. There is imaging methods. So like there is back projection, polar format, and then range Doppler, phase history. So each of these methods has granularity, what's the quality of the image. So again, it goes to the fact that if you have a good imaging code, you may get the full signature of the target. But if you don't use a really good imaging, you may lose some certain signature of a target. So for example, here, the back projection is considered gold standard image for SAR image formation, but it has imaging complexity of n cubed and computational complexity, and polar format has n squared log n, and the range Doppler has n log n, and the phase history is like just purely INQ, in phase and quadration data. So like here, like I'm trying to give you a real summary that what's the impact of the imaging scheme. So like here, as you can see, different target with a back projection SAR imagery with elevation angle 30 degree and integration angle of 50 degree, starting at 0 degree azimuth. So this is like how the signature looked like for in different types of vehicle. Now, if you change,
Dr. Mazumder, 1 second.
Sure.
Dr. Mazumder, 1 second. One more question is there.
Sure.
So Varsha, she is asking, I am working on cognitive electronic warfare as part of my internship. Any suggestions as to how deep learning based ATR could be integrated with electronic warfare?
I mean, people are using, again, like I think broadly speaking, like it depends, but like as I say, like any type of classification, yeah, you can use you can use deep learning for EW or any type of applications. Yeah, why not? So like again, EW is a broad term. So EW, if it is involved like a signal only data set, like as I say, there is you can apply deep learning for signal classification. So if it is EW is with that you want to prevent some or defensive or offensive, how you would like to do it, you can do it. So like in overall SAR or radar automated target recognition. So when it comes for adversarial machine learning, so that's actually like more of a how you tackle, like if you have lots of noises, if you have different types of noise, how you deal with that. So yeah, so obviously, like it's a growing field, but like as I say, many of the things if you have not seen what I'm talking right now, is because like this is not we can we can apply, and also these are not open literature things, so therefore we don't see those things much. So I think somebody asked, like can we ask the questions maybe at the end? So yeah, maybe I have so many of the questions, like if maybe at the end we can answer those questions. But if you have short questions, yeah, please feel free, so that we can touch the materials. But I think some of the questions has been asked. Yeah, these are good, but I think maybe if you see the full full pictures of the talk, and then you may already get many of the things, the answer. So, but I'm fine with answering now or later. But maybe we can, for the saving our time, so maybe we can answer those questions at the end. So,
and also, Dr. Mazumder, if you want a 5-minute break, because we are having 3 hours of marathon sessions, so if you want any break at any point of time, some short break, let me know. Yeah.
I'm fine. Thank you. I'll continue. So yeah. So this slide 45. So yeah, we are trying to show that how radar signature look like, integration angle and of 20, 30, 40, 50. Again, in our eyes, we don't see much difference, or like it's very hard to see the subtlety. So that actually brings you what the deep neural network can bring you, that like as it's select the features. So the certain things that we don't see at all. And interestingly, like say if you like as I say, radio frequency fingerprinting or IoT of things, detection and classification. So over there, like you just make a spectrum of a signal, but you don't see really anything whatsoever. It's like kind of this type of imagery. You can see the spectrum, but like somehow the deep neural network, they can actually distinguish the signature really detail. So yeah, here is another example of if we have an elevation angle of 30, 40, 50, 60. So like again, like those of you in the audience that who really think that is a bread and butter of your career, or you really would like to know. So that the reason I brought these things in upfront, these issues like the imaging. So yeah, so those are really important, because input to the deep neural network is your image or data. So if the data does not cover the information, so you may not get a good result. So like as I said, like applying deep learning for this military or automated target recognition, we have extra burden. Like unlike the visual imagery, you get the imagery, it really look nice. But here we have to form the imagery first, so that the deep learning can give us good results. So that's the main point here. So yeah, so once you have formed this imagery, then the next thing is you can play with the various deep neural network model like ResNet 18. Then there is a MobileNet version 2, ShuffleNet, AlexNet, and AlexNet Slim. So the point here is like you would like to see that whether classification results like really vary with a deep neural network model. So without going further, the main summary is that the ResNet 18 is really a good model, but there is a ResNet 50 and other variations or wide range. There is this type of model available as well. So the point here is that if you take my word, like ResNet 18 is a good model to use for deep neural network model, and it gives you good results because it's a really very complex but very robust model. And so now let's go the performance. So like here, this slide kind of shows that here, all of the data that we have for training and testing in scenario 1, we have randomly kind of shuffle that, we'll take 80% of the data, which is like general, in general, you take 70 to 80% of the data for training and 20 or 30% for testing. So here you can see that with the different azimuth and elevation angle data that we have for different vehicle class, if we just randomly take some portion for training and some portion for testing, you can see that all method like back projection, the first, then range Doppler, polar format, and the phase history. Forget about phase history. So these first 3 methods that we use, they all give us the good results. So the reason behind that is that when you have a random data set covers all azimuth and elevation, meaning that deep neural model has seen these data from all different azimuth and elevation angle for training, and also it shows for the same thing it shows in the testing. So therefore, on average, you see that you can see the good results no matter what, the imaging method like back projection or range Doppler or polar format all give you the good results. But the bar, the orange, red, and these are different type of deep neural architecture. So across the architecture and across the model, you always get good results because your training data has been random and testing has been random, meaning that the training model has seen all variations of the data from different angles, and testing also has seen it, so therefore it's a good thing. So it's like you give a student a calculus exam, you give a 5 different version of calculus, differentiation, and then in the exam you give them exact example of for testing, so everybody get 100%. But the real thing is, if you, let's say, you give you showed how to differentiate on x squared and x cubed, but in the exam you give the cosine of x squared. So in testing, students may not know the cosine of x squared. So now what? I did only for x squared. So in the testing, they get lost. So the real way to know how deep neural network model is that you have to vary the azimuth and elevation angle. So yeah, in this case, scenario 2, we have a training elevation angle of 30, 40, and 60, and testing on elevation angle 50. So because 50 elevation angle was not seen for training, so you can see the results vary across imaging method and also deep neural network architecture. So the conclusion is we have to vary the training and testing data set to see that how the algorithm performs across different models. And also in this case, we also vary the imaging method. So we found that back projection and polar format, they perform pretty roughly the same, and ResNet 18 is also really a good one, but the TruffleNet version 2 also worked pretty good. So the basic conclusion is that you have to have a good deep neural network architecture, which in this case the ResNet 18 is a good one. And among imaging method back projection, polar format, and range Doppler, you may be good with a polar format algorithm, which is n square log n complexity, versus back projection is n cubed. So you don't need to spend very expensive imaging method for the SAR ATR algorithm development. So the next step is to know all of those things. We have to do something called confusion matrix analysis. So here is the confusion matrix analysis of different kind of algorithms, imaging algorithms, and also different imaging methods, and we also vary the data collection, the elevation angle. So the reason I bring in these things here is that part of the ATR performance, you have to really do a thorough analysis of the confusion matrix and how the target kind of behave. So in this case, you can see it's a back projection from the imagery, and we did a training on 30, 40, and 60, and test on 50-degree elevation, and you can see the accuracy when we varied the testing angle. Accuracy really was good on random training and testing, but once we change it training on 3 angles and testing on a special angle, like in 50, and in this case it's 40, we saw that, the performance degraded from 99% to 82%. So that means that, again, when someone give you results, good results, so I have my ATR and it gives me good results, but you have to scrutinize good results in terms of what? Did you change the elevation and azimuth angle, or there are random, or you use particular angles, so that those has to be known. So the next slide, again, polar format imagery. So again, the confusion matrix to the right, you can see that random training and testing, we always get close to 100% accuracy. And however, when we change the testing angle with a different angle, and the performance really degrades. So same thing for range Doppler. You can see when the random data, accuracy is almost accurate, but when you change the testing angle, and your performance really degrade, like 70%, 74%, and here it's 54%. So now, one thing interesting to see that with this range Doppler method, when you have testing angle is 50 degree, but training was 30, 40, and 60, you get 74%. However, if you change the testing angle to 60 degree and training on 30, 50, 60, accuracy really further dropped. So why that happened? That thing happened because of the fact that when you do that training, when you do that training, something like some of the angles are very, very important. So in this case, 40 degree was very, very important for this particular target. So therefore, even you test with 50 degree, you get little better results. However, here you do not have the 40 degree for training. So basically, that particular angle for this particular target was very, very important. So therefore, because I did not include it into the training, the performance was really bad. So this confusion matrix kind of gives us lots of information, what happened, what kind of performance to expect for a particular target. So again, phase history, the reason we bring phase history into the consideration was that, okay, well, can we do radar based object recognition just using phase history, not forming an image? So, but as you can see, when you have testing angles are different, their performance is really bad. So the phase history to consider, without forming image, it may not be an option. We always have to form image. So the phase history is not good enough for classifying an object. So yeah, so the basic conclusion is if you have to start from the scratch of ATR, you have to form an image. So the question comes, what kind of image method you use? So the back projection, like as a gold standard, we may not need them because it's computationally expensive. So we may be good with polar format imaging. And also, we have to vary the elevation angle for testing. We should not just take random, angle for training, random for testing, because in that case, accuracy will not be good. And even though I mentioned MobileNet version 2 was good, but ResNet 18 is always a good model that you can use. So yeah, so that was like a single target classification. So the single target classification means that it's a, target is an image chip. So, but our goal is really not the easy problem that, okay, we can expect only single image and we like to classify it. In real world, we like to classify an object in SAR imagery that really has lots of targets, and we'd like to classify all of the targets. So that's what I think multiple target or object classification. So the input here is full frame multiple object SAR imagery with clutter, and we can have a metadata for ground truth information. So the process is like we do first detection and then we do prediction. So the detection involves, you have to pre-process that data to reduce the clutter, maybe, but maybe we don't need pre-process at all. Then we do the detection, and then after detection, we put the detection for classification. And the output is like the, where we find the target, which location we found the target, and what type of target it is. So yeah, here you can see, first we have the SAR imagery, and then it has lots of target, and then we have a detector that chip out the particular target, and then it also chip out the targets, and then it's also find out what's the location of the target in the image, and then put the image to the classifier, and then declare a target. So yeah, here in this image, like slide 56, you can see that this, like you can see more of the target over there. There is shadow and there are lots of clutter. So yeah, so this is like a typical designation of how the SAR image look like, and then and it's like an XML file to recognize the target. And so next slide. So as you can see, the SAR imagery, real SAR imagery has lots of clutter. So the first step is, do you want to do anything with that, reducing the clutter? The reason behind that, if you can reduce the noise and clutter, is that this will allow you, lots of false detection. It will reduce the false detection. So one approach to reduce clutter or speckle noise is that you can use actually wavelet decomposition, and that actually can reduce some of the clutter here. So I'll go quickly that if you we have seen that if you apply like the 2D wavelet transform, and it actually reduces your some of the clutter. So which in the detection process, the clutter could be considered as a possible target. And then once you pass those possible target for classifier, and it may falsely say that, oh, yeah, it's a target. So therefore, if you can reduce the clutter, which will reduce the detection to low, so you may have less false alarm at the end. So that was the main reason. So now, once you have do the pre-process, then the next step is like a kind of how you do the detection. So the one approach, like a pretty, I think it's a kind of old approach, like CFAR, constant false alarm detector. So meaning that you go a particular region and then take, like, say 20 by 60 by 30 or 60 by 60 pixel area. Then you slide around. You look for a bright pixel and look the neighborhood, and if you see lots of bright pixel, and you may declare that there is a target over there, and possibly keep out that position as a possible target. So that's how the CFAR detector works. So yeah, so once you do the CFAR, you pre-processing and CFAR. So like in the slide number 59, it kind of shows some of the details of the detected target here. So yeah, one thing you can see that the image to the top left is all the bright pixels is actually a target, and to the left corner here you can see there are lots of dots. So these are actually clutter, and once you apply the wavelet transform, you can see that image the last I think bottom right. You can see that here, like some of those dots has been reduced. So we kind of think that if we apply pre-processing, it may reduce some of the clutter and possible targets from the imagery. So that's the benefit of the pre-processing. It may reduce the clutter or noise so that you can have less detection of a false target. So therefore, it may reduce the false alarm or a possible target. So yeah, so once you have the detection then you design a custom deep convolutional neural network. And in this case, we knew that this data has 25 classes, including the father class. So yeah, you can have a training, validation, test imagery, and then do the classification. So so the output of the imagery is actually like that you have a chip, and it will say, okay, what was the location, pixel location, and what is the label, like say 22 could be T72 or it could be M2. So they should declare that where was the location of the image chip and what was its class level. So yeah, so once you have the target, so here is like one way to see the results. So the total detection in this case was 29, even though we have 25, so we have 4 extra class. So but it's like 100% detection was done. But then misclassification, it did misclassification, which is yellow. So one of them was misclassified. But like all of the greens shows that okay, the classifier was able to detect and classify the good target, but it also detected like some of the clutter as a possible target as well. So like, so these are all really clutter, but it kind of detected as a possible target. So these are bad in the sense that it kind of falsely said that this is target. So now the question becomes like, when you in a detection stage, you have to declare what is your detection rate. Do you want declaration of 90% accuracy or things like that? So like as I said, like if you have more detection and then detection is high, and when you put through the classifier may falsely say that okay, this is a target. So yeah, putting lower threshold for detection could potentially increase the false alarm. Or if you put the detection probability high, like 95%, you may miss a target. So there is a trade-off. What kind of threshold do you pick for detection? It may be good or bad. So in terms of the actual real-world application, the question is, do you want to miss a possible target of interest, or or you want to get a and then you get a false alarm, or you put your threshold so high that you really miss a target. So those are like the critical decision to make. So yeah, so this is like kind of a kind of good like an example of how you really do multiple target detection classification. So now the detection process we show here, it was like a CFAR based object detection. However, this is kind of a crude approach, but there is actually other advanced detection technique, like that is called RCNN, faster RCNN, ELO, you only look once. So those are like a different approaches. These are all in the book discussed, but also, like as I said, like nowadays this implementation and detection and classification at the same time, there are like a deep neural network implementation that you can get those code in GitHub to further experiment. So yeah, so this is like multiple objects. So now I think we have about 1 hour before 1:30. So yeah, I'll go quickly on the advanced SAR ATR. So yeah, at this point you get the flavor of what is like single target classification. These are like very easy problem, but multiple target from SAR imagery, these are like the much more difficult problem. So that's what I think what we are after. So now advanced SAR ATR, that involved like nowadays called adversarial machine learning. So meaning that like someone talking about like a EW or other things. So meaning that if somebody penetrate or do bad thing with your signal, what are you going to do? How do you tackle the noise issue while obtaining accurate classification? So yeah, we have a paper like last year, IEEE at a conference that actually describes more details on this implementation. So so the thing is, when you have deep learning, is good if you have standard operating condition. But if there is a noise and robustness and other things kind of degrade, it's not so good. So the question is how we can making it network really robust to worst case of noise. So the general thoughts are that like in general classifier you have a really straightforward line to classify objects of two classes, but in adversarial setting because of the noise you cannot make the line really straight. The classifier is not shouldn't be a straight line. It has to be like be molded into really get the classifier like to be really little bit different to adapt with this kind of change due to the adversarial noise. So yeah, this decision boundary kind of respect L infinity norm ball around the training data. So in general training in deep neural network, like you have actually one single optimization, but in adversarial training you have two of the two optimizers. One we calling maximizing and another one is minimizing. So again, like all those the details is in the book, or you can find also in the literature. So like we experimented. Let's say if we take an hamster imagery or CVDOM data, so we try to experiment, how the algorithm behave when there is adversarial perturbation, meaning that adding extra noise. So here, like the CVDOM or civil and vehicle data domes, we added extra noise, and we try to vary how they look like. So one thing to mention that there is SAR ATR community model, and that is computer vision model. So one thing to show you that standard deep neural network model, their parameters are really small, but ResNet 18, which is like a good model that I'm advertising so many times, it has so many parameters. But again, like this is really a good model, and it turns out that this model really do good in adversarial or noisy image classification. It does really good. So here in slide number 70, the main purpose here is that it's called training epsilon, meaning that when we add noise to the actual imagery, what we have seen that performance or the accuracy, like when you have 0 means that you don't have any adversarial noise, your accuracies are really good. But as you add more and more noise, like 4, 8, 12, and 20, the performance really degrades. So in particular, like the green one, I believe was the ResNet 18. So we have seen that even though ResNet 18 also do bad when adversarial noise is added, but it's like does better than other models. So the take from this is like, again, for noise or adversarial noise, you name it, that if you have a good deep neural network architecture, they can give you little better results than anything you pick. That's not true. So the ResNet 18 is really a good model. So here, like again, like we try to experiment, like we are adding training epsilon, meaning that we are adding noise to adversarial noise to the imagery, and we try to find out the accuracy. So here we try to experiment with single polarization versus multiple polarization. So I believe the dotted lines are multiple polarization, and singles are like single, solid lines are single polarization. So here, like again, greens are ResNet 18. So what we found, the dotted line as a multiple polarization actually really do better than single polarization within ResNet 18. So the other two models, they do bad, as we know, but within ResNet 18, which is green, solid is single polarization, which is here, and dotted lines are multiple polarization. So, and multiple polarization is really do better across all of the models, and including ResNet 18. That if you do not do anything, but if you just use a better model, then you can expect better results. So that's the story. So so like again, like if you experiment further, you can also do further experiment with the different types of adversarial noise. So here, like we have random noise and phase gradient noise, and there is another model like you can start like the noise. So you may not see from here clearly, but as what we try to show that if you added more noise like epsilon equals 4, 8, 16, and 32, and as the epsilon or the noise becomes more and more, those imagery really degrade. But what we saw that if you do the training, adversarial training, do as part of your training process, it recovers most of your accuracy loss. The accuracy improves if your training model has the data with adversarial input. That's actually really good. And again, ResNet 18 performs really good with adversarial training. So again, you can experiment a lot with with your signal. You can add different types of noise. You can with cubic, quadratic, sinusoidal, wideband, and you can do those type of things, and you can see how the performance degrade and what's the impact of different types of noise. And so like what we found that sinusoidal and wideband noises are very challenging, and if you use multiple polarization, it kind of do good. And again, like a ResNet 18 is also performs really good. So robustness on the radio frequency interference. So again, we try to do more radio frequency interference, and how that are those kind of changes or so once
Dr.
again,
Mazumder, one question we would like to take so that you are also getting some relaxation. So the question is from Dr. A.T. Kishore. He is asking for UAV sense. UAV means unmanned aerial vehicle. For UAV sense and to avoid detect and avoid algorithms can work for collision avoidance purpose. And in military, we have identification friend or foe. I think question is long. I'm just, if you can see, you can also see, I'm just reading. According to the automatic target recognition methodology, can UAV detection be fail-safe for massive deployment scenarios? Oh, so again, like massive deployment scenario, or for friend and foe detections, and like again, like these are loaded questions. So I'll say the answer depends. Like as I say, like you can see the overall and the complexity of the ATR system. So it depends on, like, if you have the good quality data, and if let's say if your goal is like, okay, I have a UAV system and I would like to know who is, I'm caring more who I don't know. So that means that you have to train enough of the who you don't know, right? So in that case, again, like if you have enough data for who is your friend and call rest of the people are foes, and if you have enough of those data set and you have enough confidence, your ATR is confident, then definitely you can say that, yeah, he's my enemy, and I'll make that decision to take this guy out of there.
So yeah, I mean, again, like it is possible, but like one thing to mention, like some of the operational things, I think actually you don't get those things anywhere. Nobody will tell that those information. But but the theoretically it is possible, So like one thing I like to say that like the ATR, as much it looks like to be, hey, yes, we can do something automatic, but like it's a function of so many things. What do you want to get automatic? So it's not. It comes with a price and years of development, so to speak. That what kind of works good. It has to be years of experiment and knowledge, and we don't get those results, right away. And so, but theoretically, it is possible. You can identify who is, friend and foe. And in particular, like say, if you are like say surveilling in particular area of interest, and the environment also a factor, right? So if you are operating in some area on regular basis, so your clutter environment and everything your system knows more than anybody else. Or also if you always use an X-band radar and you are expecting to find those things on X-band, of course, like your system will be knowing who is coming on that particular area. Versus if you someday you use X-band, someday you use Ka-band, so that could be really tricky for the ATR system. So in general, like if you are operating in a certain area and you are surveilling that area on a regular basis, so your ATR will be really more accurate than you just randomly train the ATR into some area, and then next day you bring to a completely new area. You may make mistake more in that situation. Yeah, so like going back to the slide like 75, so what we are trying to say that like the adversarial things are really a big kind of area of research, adversarial machine learning, but translating into a star ATR problem is really a difficult one in a way that we don't have tons of data. So the theoretical understanding that I'm talking here is like based on how far we can go and how far we can learn thus far. But like generative adversarial network and is like a big area in visual imagery and other recognition, and so but they have lots of freedom to do whatever they would like to do versus us, those who would like to do SAR and ATR. So it's we don't have lots of data to fully understand what's going on. So yeah, next slide. So like the summary of adversarial issues on radio frequency ATR. So the robustness of ATR improve with adversarial training. So meaning that actually like the bottom line here is that if you expect that your imagery should contain lots of noise, and what type of noise, it has to be incorporated onto the training data. So in other words, if you train on pristine imagery and then test on the noise imagery, that's a simple answer that you don't get good results. So those things has to be considered during your training. And multiple polarization is helpful for accuracy and robustness. And smalls and fast models are not good for adversarial training, and ResNet 18 is really the good model. So now I'm switching to a different topic. So object classification on neuromorphic processor. So the neuromorphic computing is one of the areas that you will hear more and more. So basically, the neuromorphic processor, what it tries to do is certain application. Let's say if you think for your UAV application and automated target recognition on the UAV, you may not have lots of power and also you like to make it size, weight, and power constrained system. So you need neuromorphic processors are like, to that kind of processor that gives you a low power computation, meaning that once you do a training model, and then you can bring this model to the neuromorphic processor, and the classification, can be done within milliwatts of power. So that's what I think the neuromorphic processor has been doing. So these are like like the IBM developed a processor called True North. So this particular True North hardware is actually good for target classification with a very low amount of power. So they call it like TN or IBM's True North. It's a neuromorphic CMOS chip, inspired by human brain. And so, it has a a simple chip can have 4098 cores, as a 64 by 64 tiled array. And each chip has 1 million neurons and 256 million synapses. So I will just quickly go through. So they in the True North, developed by IBM, they have 3 different versions at that time, but they are becoming more sophisticated at this point. So the NS1E is like it's a processor. It has a Xilinx FPGA with a 2 ARM core, and so it's really very low power. It consumes really low amount of power. So then they have another NS1E-16. So basically they combine 16 of them together as a as a cluster. So that can actually do more image processing task. And the NS16E is a more of an integrated version of a 16 of this True North processor. So the bottom line here is that the way a regular deep neural network works, they try to mimic the same type of computation in a True North. So we talk about like convolutional neural network, CNN. So they try to mimic that same type of neural network here for this platform. It's called Eden, an energy efficient deep network. So they basically try to implement convolutional neural network for this North chip. So let me go. So the process here is like, again, like you have a training data set. So they basically have a way to combine all of this training data set called LMDB format. So LMDB, I think it's called Lighting Memory Database. So they make a big data for training. So again, like these training are done offline, meaning that this may take times, hours, or days. But once you are done training, it can save the model that could be used for classification within a very real time. So yeah, so the entire classification task is you create a data set file called LMDB, and then you do the necessary pre-processing, meaning that you can add noise or you can do rotation and translation and things like that. Then then you make the network and you train it, and then once your training is done, you have a trained network for testing data and evaluate the performance. So so yeah, here is slide number 86. Is like kind of shows like this is the True North chip, and you can integrate with your with a GPU based system, and you can do the classification. So compared to the MSTAR target classification, so you can get pretty much similar accuracy, like about 96% or 97% of the standard classification accuracy. So the reason I brought into that, okay, energy efficient computing for size, weight, and power constraint. is important, and so this is what IBM has developed with this. But nowadays, there are other things also coming up, like Intel, they develop a chip called Loihi, so that actually can do the classification with a low power, consuming low power. So yeah, so that's kind of the IBM True North processor. This is called neuromorphic computing. So like if we go to the future research where we are heading, so the transfer learning or domain adaptation is like one of the big area of research. So meaning that if you use 100% synthetic data for training and testing with measured data, what kind of accuracy we can get. So that's kind of the big area of research because the fact that we can make lots of synthetic data that as much we want, we can change the articulation of an object, but that could be done very easily to transfer learning. However, the issue is that synthetic data are more pristine and they don't resemble as the measured data. So therefore, the research has to be done, how we can make transfer learning works. And then out of distribution detection and classification. I think that's actually the question that someone asked, goes to, okay, well, friend versus foe. So friend versus foe, we can actually think and differently. So meaning that if we have if we consider for 10 targets of interest that we would like to know, and now we got an 11th target, so meaning that the 11th one could be an enemy. So in this case, the out of distribution, meaning that if it is a different target, can the automatic target recognition system can identify that it's a new target, or it will bring to my original 10 targets class. So that's kind of it's called out of distribution detection and classification. So meaning that I want that my ATR should be smart, so that if it's a new target, it should reject it and it say that, okay, well, I have not seen this target. And so that area has really it's a challenging area in terms of false alarm, and also if it's the new target, could be a confuser, and it should declare that it's a confuser. So the out of distribution detection classification is actually a challenging area as well. Then one of the biggest area is real-time training. So you don't want to train for 2-3 days or even 2-3 hours. You want that, okay, well, you have a system that's going to the operation, then you would like to get it done training as fast as possible. So the question here is okay, well, we know that as much data, more data is good for training, but can we know what are the data, what are the most important data? So as I say, if we have a target of interest, if someone say, okay, more data is good, is it for one particular target, do we need 500 imagery to train or 1,000 imagery to train? So actually the question is not that you have 2,000 imagery could be good, but actually better to answer is okay, well, I need number of imagery that actually capture all the features of the target. So that kind of answer the question that, okay, well, we have seen that during the training process, 40 degree could be very important for some targets, but for some target it may not be not so good. So it depends on the target, that you have to capture some of the elevation and azimuth angle to make sure that that we have maybe 50 imagery is good enough, but it should cover the entire most important features of the target. So then nowadays, again, like it's what called on-chip, online, or power efficient learning hardware. So new things coming up called memory store, neuromorphic computing, and Intel Low EE. Those are like a very kind of a low power computation. Like again, like if you go back to the UAV or other system you're thinking about, so you don't have lots of power on those kind of systems. So that's why like the memory store is like a new types of processor coming in. And then a new computing and is other, and Intel Low EE is already in the market. And of course, like NVIDIA, they are also selling like $100-$200 compute system like GPUs for getting the training in as fast as possible. Then there is a multiple like you have SAW and electropic imagery together or fusion to get the target recognition. Then there is a next things coming up, quantum machine learning algorithms. So as you know, quantum computing is the next kind of things coming up. So there is things going on how the machine learning algorithm could be implemented on quantum processors. So the quantum machine learning, there is a QCNN, quantum CNN, quantum convolutional neural network are under development. So those things will be coming up. Then there is a like the SAR ATR complexity analysis. So here, like as I say, like so ATR is again like it's not that is a kind of silver bullet that we can develop some systems, so therefore we call it ATR and it's we solve the problem. No, I think ATR is like depending on how robust the system it is. So let's say if that are objects or targets of interest are in open field, so it's called test target signature. If it is an open field and no articulations, and those are they are fully separated from each other, so these are like kind of easy problem. So but if the targets are very adjacent to each other, closely each other, and they have different layover and all of those issues, those are like with the clutter, so those makes the ATR very, very challenging. So the bottom line is like the ATR, as much it shows that okay, we want a machine to solve all of the problems, and however there is trade-off, how good an ATR could be. So it depends on how robust you would like to develop. So having said that, I'm not trying to be everybody fearful, don't embrace ATR, but the truth is like you could be very conservative how your ATR system works. Therefore, you try to be as robust, and therefore, at the end, you can be really thoughtful that okay, yes, I made my ATR really robust. Versus like okay, well, I developed something, it works 90% of the time, and 10% of the time it doesn't work. So if we are happy with that, maybe we have to live with it. But in general, to making it robust, it has to be experimented with, very difficult problem set and difficult, operating conditions. So I think that's all. And I think before somebody asks questions, I'm just asking a very popular question. So like many people, like as I say, people ask that okay, well, how do you trust results or classification accomplished by the deep neural network, and is this a black box, and what is the validity of these results? So I think I try to answer those questions from the beginning, that it is true that some people are not comfortable the way the decisions are made, like from low level feature and aggregation combining or fusing all of those features, and therefore this is what it is. But like as I say, like DARPA has a program called XAI, Explainable AI. Then there is a CAML, like competency AOR machine learning. So mean that every step that ATR making the decision, it should tell us why it's making that decision. And then there is a program called GUARD, guaranteeing AI robustness against deception. So those programs are trying to answer those type of questions. But in general, like as I said, like we are going into the third wave of AI. So human-computer interactions and explainability is kind of if you're trying to know more about how the ATR making that decision. And another question people ask, okay, what's the ethics of applying AI, ML, or DNN for military operations? So like as I said, the whole idea that we are trying to cover like 7 habits of ATR is the main reason is that we should add we should make those ATR system robust, and also we should be as conservative as possible, so that we shouldn't be happy with that whole problem solution. The solution should be more comprehensive, so that it kind of avoid all of those ethics that for military operations or so on. So I think having said that, I think we have time for answering questions. So yeah, thank you for your attention. So please go ahead for the questions.
Thank you, Dr. Mazumder, for very, very nice and exhaustive presentation. I can say continuously from 2.5 hours to I think almost 2 hours 40 minutes you are speaking. Friends, if you are having any questions, please type in the chat window or Q&A window. We will be having sufficient time. I think we are having still 20 minutes of time before sending the next speaker. So you can clarify all your doubts. And Dr. Mazumder is very, very generous. He will be taking all the questions till next 20 minutes. I can see one question popping up here, which says that how effective is a combination of a radar target simulator and GANs in dealing with availability of diverse data and achieving robustness?
Yeah, so like like one approach is I try to touch like is a multiple intelligence fusion. So like say like if you have SAR or radar, you combine with electro-optics or video imagery or other type of information. So if we do the fusing those information together, that could be a good thing. So even though like the basis for utilization of radar is for all weather, but weather is not in general bad all the time. So the visual imagery and others could be helpful. It can actually increase the confidence significantly. So the multiple sensors, combination of multiple sensors could be really a good thing to reduce any doubt, for making ATR more robust.
Okay. Another question is kindly also touch base on dual use cases of UAV system.
Say it again.
Kindly also touch base on dual use case of UAV system. Dual use case of UAV system.
Dual use of in terms of what are the dual?
I think for civilian as well as military application, I think they wanted to know more on that for UAV.
Oh, so like as I said, like now I didn't say anything. So the UAV utilizations, like nowadays, obviously, like say, like military applications of surveillance. I think it's everybody knows that people are using for military applications, and civilian applications of UAVs are like different things, like say mapping an area or vegetation or disaster planning and things like that. So I think like when you say ATR, we not necessarily mean that all we are looking for the bad guys, but also for disaster planning, or knowing that if there is a rescue operation, how we can find people in certain area. So that's also the applications. So in general, yeah, like say that's why like I know some people they are not comfortable to use the word target. So sometimes people consider the recognition object. So object recognition is sometimes politically better word used. Yeah. So for rescue mission or any of the peaceful operation like to finding, or even like you can consider the security operation or surveillance is or could be a good thing in a way that you don't want the bad guys. Somebody should not be stealing something from somewhere. So yeah, it's like the UAVs for automated target recognition. It could be both civilian and military applications as well.
Thank you, Dr. Mazumder.
I think somebody asked what hardware do you
Yes.
suggest for training, GPUs only, or even Intel is having AI hardware. Yeah. So again, like these are like competitive vendors. So like as I say, like if your system actually can afford like GPUs, like if it is like 10 watts of power, then it's a good thing. But really, like the NVIDIA and Intel's AI hardware, so it's a competition. So like I guess it depends, like what be suitable for your applications, like so it could be either or even some people they use FPGA as well. So but like I think these are kind of more of a your choice, how what kind of things you'd like to use, or even like a Google has called something called TPU, Tensor Processing Unit, and I think people can rent for training purpose as well. But like as I say, like training is part of the process. So in many cases, maybe you'll be fine if it takes 2 or 3 days for training. You could be fine, and then you can use that model for testing. So it doesn't have to be that like a sophisticated training hardware all the time.
I think now I would like to request Dr. Lakshmi Madam to summarize and provide her perspective, and after that, Manisha, you can conclude.
Yeah, firstly, I really thank Dr. Mazumder for a very comprehensive talk he has given. I mean, it has given, and as we could see, he has covered the entire gamut of AI, MLDL techniques, and the practical experience that he has brought in is really noteworthy. And I am sure out of the audience, everybody, I mean, many of them will really apply these in their work and will see the results. So, and I once again compliment the organizers for arranging such a good talk, and thank Dr. Mazumder, and I hope you will be also taking some mails from people if they are really interested. So if you can share that, then that can be, I'm sure a greater interaction will help the community in India, and so we really thank, and you have covered from, I mean, all topics from machine learning aspects and the deep learning for the ATR, covering the theoretical and the algorithmic as well as the practical aspects, and especially bringing the energy efficient aspect, which is more required for actual, implementation on, say, mobile applications, or maybe even for airborne or space or UAV applications, where all these resources become very, very scarce. So it's a very good, excellent talk, and we thank you for on this group of IEEE as well as defense and space scientists. Thank you.
Sure, absolutely.
I would also like to thank Lakshmi Madam to accept the invitation and grace the occasion. And definitely, it was a pleasure to have you, Madam, and Dr. Uttam Mazumder, sir, because it was really a great talk, and I think it met more than our expectations. And we will be, if any, I would like to have your mail ID or something, so that in case any offline further questions or queries are there, that we can share and talk. I will just discuss it with my colleagues. And it was a nice talk. I think almost all the aspects were covered. And I would like to thank Puneet also, because it was a request from him that I want someone in this area. And he has
yeah, thank you. So I actually have my contact in my my slides. So yeah, so feel free to contact me. My pleasure.
Yeah, so thank you very much to all of you. I will just summarize again on behalf of IEEE. So in this wonderful lecture, I will tell DL, recent advances of deep learning based radio frequency, SAR target detection, and future technical challenges were presented in detail, very, very exhaustively. Some of the important deep learning architectures and their benefits to SAR image classifications were also discussed. RF databases for deep learning research were presented. Then recent research results, technical challenges, and directions of deep learning based RF target classification were explained. Finally, adversarial perturbation to mitigation techniques involving SAR automatic target recognition were provided. Implementation, most importantly, implementation, demonstration of Google Colab, Amazon Web Services was the cherry on the cake. So thank you, Dr. Mazumder. And on behalf of IEEE Bangalore section and on my own behalf, I would like to thank you very much for joining us. And I know it is midnight for you, but still you are awake and taking all the questions and explaining us from last 3 hours. Along with you, I would also take this opportunity to thank Lakshmi Madam for joining us and continuously sitting us and providing her perspective as well as interacting with the speaker. So thank you, Madam. And we still hope you are going to be another 1 hour, because we have brought you another very, very excellent lecture on RF measurement facilities, where whatever Professor Mazumder has spoke, we are going to see that how all these theoretical aspects can be measured in reality. So we are also having our next speaker, Richard Liu. But before going to him, we will be concluding this session. Thank you very much, Dr. Mazumder. If you can stay with us another 1 hour, that is okay. Otherwise, I will not stop you, because I know it is a midnight for you.
Yeah. Okay, thank you. Yeah, so again, thank you, and please feel free to contact me if you have questions. So I think somebody wanted the slides. Yeah, I think it could be available, and also many of the things are discussed in the paper also available. So I think the papers actually has more details, so to speak, how it was done. So yeah, thank you so much.
Thank you very much.
It was a pleasure. Okay, thank you so much.
So friends, after with this wonderful lecture, we are going to have another very, very exciting presentation from Richard. He is already there. So I will just introduce about Richard, and then I will pass on the presentation ball to him. So Richard Liu has established the WavePro in 1993 as the first EM test company in Taiwan. Prior to WavePro, he graduated from National Taiwan University in 1988. He volunteered military service in NCS IST as the manager of Compact Range Test Lab to develop EM test system for military applications, including RCS, radar test, and various antenna pattern test for 6 years. Based on massive experience of EM test system installation and test, WavePro has developed superior performance compact antenna test ranges for ultra-accurate military applications since 2009. Also, he developed ultra-broadband compact range, which has been accepted by many famous base station antenna players for 5G applications. In addition, the CAT compact range from WavePro has been certified by Qualcomm for 5G test. He also has devoted to serve EM Society in Taiwan wholeheartedly. He was the vice chairman and chairman of Taiwan Microwave Association during 2013 to 2015 and 2015 to 2019 respectively. So, Richard, welcome you on board. And now I'm passing on the presentation ball to you. You can share your screen.
Okay, I'm trying to find out how can I share my screen.
So you just look below.
Yes.
There will be three or four tabs. There is a share button. Yeah.
Okay, I saw it. Okay. So that would be this one. And so coming back, I will share the screen. My screen to yeah.
Yes.
Okay.
We can see your presentation.
Okay. Okay, that's my honor to have this presentation to introduce the measurement facilities for AESS AOA, AOS angle of arrival, and other defense applications.
You can go to the full slide mode, Richard.
Yes?
Yeah, you can go to the full slide mode, then it will be much better.
Okay.
In the presentation mode, you can go.
Okay, so can you see well?
Yes, we can see now.
Okay. My talk will talk about two kind of technology. Main technology, one is anechoic chamber technology related, and the second will be related to compact antenna test range. Okay. For back to the anechoic chamber technology, I will introduce 4 applications. It's a low frequency application. The first, this is the low frequency application, down to very low, like 100 megahertz or 200 megahertz chamber. And the second is high length, very big, large length to high height ratio chamber. And the third will be the HARM, the high speed anti-radar radiation missile. Yes. And the last will be about VHF antenna measurement using the optical OE converter. Okay. And the compact range, we'll talk about the compact range application, the four applications. Okay. And if we have time, we'll talk a little about satellite. And about the defense application, the angle of arrival is a very important parameter, because all the tests we try to generate a stable plane wave, that is mean the angle of arrival to measure the performance, no matter tracking or define the direction finding. So the angle of arrival would be very important. So here you can see this. If we generate a plane wave to the AOA in the blue, and if the range we have a cluster, we call the AOA arrow. You can see that the cluster label the cluster level, you have to be very, very low, small the cluster level to have a good, small AOA error. Okay. Okay. So before the first application, I will talk about the low frequency anechoic chamber. Normally, the low frequency anechoic chamber, you need to have a taper chamber to control the scattering of the absorber. But the taper chamber, this problem is you have to be very stable phase center to feed the taper chamber. Then you can have a quiet zone. But our design is better, much more stable and better quiet zone. And based on our design, we can go down to like 100 megahertz. Okay, this is our patent anechoic chamber. We don't use the taper chamber, we use the rectangular chamber. We control the scattering of the absorber from the feeding wall, and we can achieve a very low frequency. Like this one is only a 6 meter chamber, and the height is about 3.5 by 3.5, and we can go down to 300 megahertz. Actually, this is our in-house chamber. Okay, so this is the quiet zone. We can see even down to 400 megahertz. The amplitude ripple is very small, and the amplitude taper is small. So it's pretty uniform, very uniform quiet zone for testing at the low frequency. Okay. And this is a test case. Actually, this is a shipborne communication antenna. Our shipborne is a military antenna for the communication. Shipborne is 235 megahertz to 385 gigahertz. So we test in this chamber, in this our pattern chamber, and we can get a very beautiful 3D pattern. And you can see that this 3D pattern, you can see here the lower backlobe, here is the backlobe. You can see the backlobe. The backlobe have some like a pumpkin shaping. That's because this antenna, the ground is actually this like the slip dipole. The ground is by the section wire. It's a metal wire by the section. It's not a circle, so you can see the diffraction of the wire very clearly. It's 8 pieces, 1, 2, 3, 4, 5, 6, 8 pieces. So the tiny diffraction of the ground, we can test it. We can find it out. So it's a very successful one. So in this kind of chamber, we can measure 235 megahertz. Okay, this is the low frequency technology we have, and we think it's very unique because it's very stable and easily to build. And we have the patent that in US. Okay. So later, if you are interested, we can talk about that later more. And this one is for the missile for high power testing, because the high power testing, the first you need to far field range. It's the far field anechoic chamber. It's far field range, so the distance is pretty long. This is 20 meters long, and the height is only 4 meters. So the ratio will be 5 times ratio. Normally in the anechoic chamber, the better you only 2 times, twice, like 4 meters is better only 8 meters or even 9 meters, it will be very long already, because the gradient angle will in the absorber, when your energy of the normal of the absorber, you are scattering. So in this case, we using 2 technologies. One is using the absorber scattering control. We align the direction of the absorber to, if there is scattering, we don't want to let it scattering into the quiet zone directly, and we let it bounce at least twice. Then that will be attuned good enough. Another is on the 4 edge, we using the arc. we're using our car to block the corner reflection. This is our car technology is from Ohio State University. We cooperate with them and transfer the technology to Taiwan. Yeah. This is the long range. So you can see it's a very, very nice empty repo. I put it in each 1 dB for the is half dB for each frequency. So the repo is plus minus 0.2 dB. Okay, is this kind of popular range is we are pretty satisfied. Yeah, we are pretty satisfied for the result. And this is the home AOA production calibration system. You know the home is broadband is very broad, like 2 to 18. Okay, even broader. And the commonly using the form spiral, but the pole sighting, I mean the angle, because it calculated by the sum and difference pattern, but it is very frequency dependent. It's very frequency dependent. So we need to calibrate each angle of arrival of each angle and each frequency, and put it into the table. I will show you let me try to go. Is sharing? Is sharing? Let me share.
Richard, you have to share video files separately. It will not play here. Yes.
Okay, I'll share my screen. Is that right?
Yes. Yes.
Okay, that will be good. That will be good. Okay. So okay, this is we're using the robot, and we calibrate the robot, and we measure the AOA of the because even the anechoic chamber, they still have an AOA error. So we calibrate the AOA of the chamber of each frequency, and we measure each frequency and each angle of the home, and put the data into the home to calibrate the AOA. So in that case, then we can be able to find the direction of the radar accurately. Yes, and because it's it's a production system, and you need to calibrate each angle, and you have to calibrate each frequency. So it's it's a massive measurement. So we do this kind of system. Actually, we are building the second system, maybe even more, because it's a part of the production of the home. Yes. Okay. So this is the production of the home. Yeah, and the technology is first we need to have a very stable AOA, low scattering and cold chamber, and then you need to calibrate. It's just tedious. You need to calibrate each frequency of the AOA, and you have a precise position. Then, and also you need to control the interaction between the chamber and your missile, and then you can build. Then you can have a good accurate measurement. And also we using a continuous scanning because to shorten the measurement time. Yeah. And we need to each one we need to calibrate. It's not, you cannot just say, okay, I approve that it's okay and using the same data. No, each one you have to calibrate. Yes. And this one is about the anti-stealth radar technology. It's because the very low frequency, 70 megahertz to 700 megahertz. If you build a large, VHF array antenna, and you want to measure the antenna, because it's large, so you cannot use an echo chamber to do it. And normally using the near field technology. But the near field, the problem is the near field, you have the probe and you have the structure around the probe. We need to have absorber to reduce the scattering, and also the arc cable of the probe. The unbalanced current will radiate, so the probe pattern will change. All these things have difficulty. So our idea is we're using the OE probe. Okay, this is we can see the here is let's see here. This one is a higher frequency. It's 700 megahertz. The 700 megahertz probe is less than 1 centimeter, and so we're using the probe. It's the E-field probe. And we convert the E-field to the optical. We convert the E-field to optical, and we have we modulate the laser and we demodulate the RF. And because the E-field is weak, so we have the low noise amplifier on the antenna. So we have another fiber to power the low noise amplifier on the probe. So then we can have a very good dynamic range. We can see here we are testing in the thin cell because it's low frequency. The thin cell is very low frequency, generate the E-field. Yeah. So we can see from here is this one is 70 megahertz. I believe that is 70 megahertz. We are testing. This is S21. We transfer the energy from thin cell and receive from the EO probe and modulate the laser coming back to here and demodulate and going back to the PNA. So you can see is S21. Here is S21 only minus 14. So it's a very low loss. So we can have a good sensitivity. And we actually, this one, we are testing the uncertainty. You can see the uncertainty here is around the plus 0.05 dB of the uncertainty of this test setup. Because we need to have a very stable ambient phase, then we can, using a near field technology to transfer the pattern. And you can see here is the probe. E-field probe. It's we put the wire is vertical, horizontal, vertical, horizontal. So actually we can catch the polarization, the field, very pure polarization field. And this structure actually is formed. It's air. It's direct constant 1.03. So and it's low profile. So we don't need any absorber because when you go down to 100 megahertz. The absorber is more than 1 meter, and it doesn't make sense to put the absorber on the probe because that will kill you everything. You cannot measure that. So we put this invisible. We say the low profile probe, then we can do the near field accurate near field measurement. Okay, this is about the low frequency antenna array. Thinking that MEG they're using the still similar Vivaldi probe, but they put the absorber around the probe. And the back structure, we don't think that works because the probe coupling and the back structure interaction at the 100 megahertz or 200 megahertz, that is very huge. So that we're not able to in the right field. Okay. This is about the VHF array antenna measurement, and then we are talking about compact antenna touch range technology from WavePro. Okay, now actually we have a pretty good shipping to the whole world, and I believe 40 to 50 compact ranges delivery. And we using the brand Roach technology from Ohio State University, and we are flexible and knowledgeable design, so we can design the different applications we have to develop. Here now we have certain designs, different designs, to fit a different application, like automotive radar, or RCS, the antenna, the base station. The base station have FR1 and FR2. They all are different. So we have many kind of different designs, and we are pretty quick. We could design flexible to design what you need. And special thing reflector is very stable. We said a closed box reflector. It's very accurate. Later we'll see that. It's a wider temperature range and without gap, and it's the box module. So we have the special IP to make the temperature stabilization for the large compact range, because when you large compact range, the temperature control will be a big issue. Okay. And in the middle side, we're using a single body. Okay, let's see some picture. Like this one is 3 meter by 3 meter compact range. You can see actually it's a single body. It's a single body, and it's a box. Inside is a hollow frame. So it's closed body, so it's very robust. So like this mouse is a plastic. It's soft, but it's a closed body. It will be very rigid and robust. So the closed body will make your body structure very stable. And once it's very stable, we can machine it or trim it to very precise. If it doesn't stable, then you cannot do that. So, and the good thing is, so we can go down to the surface area of 15 micrometers. So I can upgrade to 100 gigahertz, 200 gigahertz, and have very good phase information. Like this one, this is test result of this reflector. At 39 gigahertz, its empty ripple, you can see plus minus 0.1 dB. Oh, okay, it's a 0.1 dB empty ripple, and the phase, because the phase would be the most important parameter for the meter application, because the phase means the AOA, the angle of arrival. And you can see the phase here is 1.5 meter quadrant. This area is only plus minus 1 degree, plus minus 1 degree phase area. So in this case, we can measure the angle of arrival precisely. Especially this is for radon. The radon you are talking about 1,000 degree diffraction. So we need to have such beautiful phase plane wave. Then you can measure you can really measure the pin diffraction down to the 1,000 degree. And this is crossfall of the reflector. So we using this camera. We using the. Sorry, I'm coming back to the picture. We're using the box design. It's a box. It's not panel. It's not just a panel. As a panel will change the temperature, and we're using the box. That will be stable and very long life and very accurate. So let's go to introduce some application of the cater. The first is the AOA calibration, MISO AOA calibration, and the function test applicator. You can see here is we a chamber like this, and we can put this is the MISO. This MISO without radar, and the seeker the ground will slide in, and we align the AOA. So we generate a plane wave, and we using the we say the multi-target head MTH is provided the pitch and yaw, and doing the pitch yaw receiver tracking, and the tracking response and the calibration. Also to see if when we the target jumping, can you do the tracking to see your tracking receiver how it working, and you can do the target simulation and do the perform the EIRP measurement. It will be very precise because the compact range loss is very precise, so you can measure very accurate EIRP of the missile. Okay, this one is shown is 6 feet, 1.8 meter cone-fed compact test range. Okay, and this is another also for the missile application. This one compact range is for the AOA alignment, because you need to align your final AOA with radon with the seeker, and you can you generate a precise AOA, then you can align your missile. And in this case, you can see our reflector is such accurate like a mirror, and so we can have such good 1 degree phase error, and in this case we can make we can calibrate the AOA. This one is about for hardware in the loop testing, and same thing. Hardware in the loop, you need to have the framework far field. Your framework. The compact is the best, and I think that the compact is providing a very good far field. Is you can generate like 1 degree is 1 kilometer. Like this is you can the effective difference is more than 1 kilometer. That means that in your lab you can generate 1 kilometer far away signal to here to have the quality. But in this case, then we are same thing. We're doing the multi-target, and also important thing is we need to have a very low backscattering refractor, because if you measure the power in the loop, you transmit the power to the refractor. It's a big, huge metal. If the reflection coming back to the seeker, will burn out your receiver. So the compact range itself have to be very low backscattering. And you can see from the time domain, actually here is the reflector, and here is the feed antenna, the feed and the mismatch of the feed antenna itself. So you can see our reflector is almost is very, very low backscattering. Okay. So this is design is a very, very low backscattering of the reflector. It will not generate the echo to damage your seeker. Okay. And also one more thing is we need to have a very stable AOA tracking versus polarization, because in the hardware in the loop, your missile will rolling. Not only pitch yaw, also you are rolling. Once rolling, the AOA will change it. If the change it, the seeker will jiggling. Yes. So we could have a very low AOA stable AOA tracking. I didn't show the result here. It's about 1,000.005 degrees. 0.005 degree AOA diffraction when you change the polarization. Okay, so that will be mostly important thing is controlling. The first is the component design, and then you have to control the anechoic chamber, everything very well. Otherwise, because the scattering is very polarization sensitive, when you change the polarization, the scattering will change. So your AOA will change. Okay, this is for our for the power in the loop, and we using the technology is color imaging. It's video imaging, color imaging, so you can see we check the frequency and we scan in the field, and we can get the angle and the downrange image. So from here we scale to -50. There is only the plane wave source, and the whole chamber are clean. So that means your plot is less than 50 dB, -50 dB. So it's very clean of the chamber. Okay. Okay. Sorry. Here. Yeah. Here is the AOA during the rotation, the polarization, the different polarization. The AO. This is the frequency. Okay. This is the AOA angle error. And last application is about the radon pole size shift error measurement. Basically, we using the semiconductor production system design concept to have a precise pole sizing for PSC measurement. And here you can see we are building a demo system. This is demo system. We are building to be finished in this month, and we'll demo that. We'll demo the pole size shift, and our goal is 0.003 degree pole size error. And this is based on the knowledge of about the scattering and all the knowledge about the receiver technology, also positioning technology knowledge to have this pole size error measurement system. This is what we are doing. The project we are doing. And later we will talk about large compact range. Because we have this is 6.4 meter by 6.4 meter. Again, coming back to the compact range, our design concept is in the other companies, some companies doing the reflector using a panel. It's the panel and using the back structure to adjust the panel to have a precise service. But the panel itself is easy to diffract. It's very easy to diffract, and it's easy to diffract. And if the back structure, because the temperature change, the back structure change, the surface will change. So we don't use this kind of technology. We're using the brick technology. Okay, you can see this 6.4 by 6.4. It just looks like a single piece. It looks like a single piece. Actually, we modularize it 7 modules. We assemble it together, but we don't have gap. We don't have the gap. Okay. The technology here is we're using the brick module design. Okay. Actually, like Airbus, they have the same, very similar concept design. It's a brick. It's not a panel. So you can see here, this is the 7 panel. This is the seven module to, not panel, 7 module, 7 bricks to assembly into this reflector. Okay. And our concept is thick, rigid body. It's very thick, like this is 1 meter, and stable, so we're able to machine accurate. And then we precisely assembly by the pin, alignment pin, okay? And the forming an accurate, stable, single body. Just looks like a single body. It's not a single body. It looks like a single body box reflector. Okay. And we sit on the, we put a reflector sitting on the back structure, on the uniform loading back supporting structure. So we don't use the back structure to align our reflector. Our reflector itself, it is accurate. It is accurate and a stable body. And in this box design, we are much more temperature stable, and so we can operate the broader temperature range. Like the large compartments, normally in the US, they just spec in ±1 degree. The largest were ±2 degrees. So the air conditioning, the temperature control was the maintenance cost will be very high, and in case your temperature control system malfunction, well, you might damage your reflector. It might damage your reflector. Okay, and we have a special IP. Even we can achieve the ±10 degrees. That means that the reflector will be much more stable, and you don't need to have a very nice temperature control chamber, or you in case some has any problem, you will not damage your reflector. So like this one, we can operate up to 100 years. Like the large compartment, you can see even the large one. You can see the mirror. Okay. This is the very specific. I think that only the WavePro and the Airbus doing this kind of trick. Yes. And let me show you some interesting photo. This is from MEG. Okay, their brochure, and they are showing the MTAG 2017. Okay, this is the same size, 6 meter by 6 meter roll edge compartment. Okay, they're using a panel. Okay, so you can see this picture is very interesting. I found it, and I downloaded it from the website. And you can see that each panel, because I believe that it's high frequency, so the gap, they have a very tight gap. So you can see actually it's already deformed, the deformation already. Here you can see the line is the deformation already. So you have a panel. Once the thermal temperature going up, the panel will push each other. Once you push each other, it will deform it, and it will not coming back. It will not coming back. So this kind of technology, using the back structure to adjust a thin panel, I think that is really not a good idea. Okay, it's not a good idea. Okay, that's coming back to, so this, because the brick, it will be very stable and not change. And about RCS, we have a partner with the ComputeQuest. This is Steve. He's a co-owner of the ComputeQuest and the Discover project. So if we provide an RCS management system, we provide a large temperature stable compartment and chamber engineering. We have in the past, we founded in 1993, and now is big and large, and around the 200 chamber here. And we have a very expertise about the EM control technology. And the ComputeQuest is famous, is really famous in US about the RCS. Therefore, 31 years RCS experience in US. And we suggest either DNA or quarter branch, the first radar transceiver, and also the Lockheed Martin choose pylon with delta signal. And currently they actually the CompuQuest and the Delta Sigma, they have 4 ongoing RCS projects right now in the US. It's actually is blocking modeling also. So this is the pylon. This is pylon. This is Roger, the owner of the Delta Sigma. We have a project cooperate together, and so they are very experienced on the pylon. And the large and the small one is like this one is the large one. This is the customer list of the CompuQuest. You can see mostly are in US with Masa and Lockheed Martin and like F-35, F-22, F-35, F-22. They are using their system, and CompuQuest they started RCS business from 1989, and mostly their service in the US. So I believe the most confidential project and built by them, and they could provide. I believe they could provide everything you need if you are working on the RCS. Okay, yeah, and this is the software about the imaging, and their imaging. They have the technology is they can remove the. They have many kind of signal processing. They can remove part of the imaging. Like if the real target, you have to some picture. And the picture, they can remove it from the image and calculate ourselves. And also, they can find the hotspot and the scattering center of the image. This is from the CompuQuest. He was here in Taiwan last month. Actually, for 1 month, he left. He just flying back to US 2 days ago. So we had a short talk with Puneet, and he's very kind. He's really willing to provide his knowledge to service to help the India. Okay, so this is about the RCS, and we have this kind of phone. If you are interested about that, we have this phone for input about the design, because we are engineering company. We can design all that you need. So we need to know your application, your quantum size, your lowest frequency. Special low frequency is very important for us, because the reflector design we actually will focus on the lowest frequency. It's 500 megahertz, 400 megahertz, 300 megahertz, or 700 megahertz, and that will change the reflector design and also the chamber design, and the highest frequency and your available space building, and your weight and what kind of position you want. I will send you, if you are interested about that, then I can send this table, and you can, if you are interested, you want me to have, let's have a preliminary technical proposal. We have this input, then we can have a preliminary technical proposal for you for reference. Okay, how many time do I have?
You are having another 10 minutes, Mishra.
10 minutes? Okay.
Yeah.
Very quick about the satellite. This is a satellite in Taiwan for most of satellite. It's horizontal near field and spherical near field. And this spherical near field, we have a pattern to, because it's the largest spherical near field. The structure we are deforming, we have a pattern to compensate the. How will compensate the sphere to have a very precise sphere to measure the accurate spherical near field testing. This is simulation for the installation before we start, because it is existing chamber, so we need to design a very special rigging crane system to install the chamber. Because the space is narrow and the door is only 1 meter. More than 1 meter, only 1 meter door. We need to bring everything into it and install everything. So this is the scanner we're building in our factory, and we installed it in the NSPO in Taiwan. Okay, you can see it's a horizontal near field. Yeah, the speaker near field also. Okay, that's all my talk, and welcome. Please, is there any question for me? Yeah, thank you.
Thank you, Richard. Thank you very much.
Yes.
For sharing your presentation as well as expertise, especially in the fields of RCS as well as defense application and including space applications. So before going to the audience, if you are having any questions, please type in the Q&A window or the chat window. We'll be more than happy to take few questions. But before going to that, Richard, I would like to know that RCS measurement and other things, they are quite restrictive technologies, which easily people will not share. But what about your company? Suppose in India, anybody wants to establish a chamber where RCS measurement can be done. Because our experience is most of the companies, they will tell that this being in ITAR, we are not able to provide this technology. So I wanted to know what is the status from WavePro?
I think we are very good on the Tampa branch, and myself, I was the Tampa branch lab, RCS lab manager when I served in military in Taiwan. Okay, and so we know about RCS well, and I built the RCS receiver by ourselves, and we have the compact range to measure the RCS, and we have experience about with the General Dynamics to measure the RCS of F5 to F5 to be the acceptance of the GD radar, GD53 radar, and I'm taking care about compact range install RCS measurement of the F5E. And another team is taking care about the outdoor testing. And finally, actually, General Dynamics using my data to the radar acceptance. So we are very fast. Currently we have in WavePro now we are 36 people, mostly are engineers, and very focused on the EM. We owe everything at EM. So in Taiwan, the 80% the missile is project is handled by the WavePro, doing the calibration range. Yeah. So during the I start from 1988 till now is 33 years already. Yes. So everything we are doing is wave. Is about scheduling. So, and for the RCS, I think the pylon, we need a good pylon. So we found the Lockheed Martin, they're using the Delta Sigma pylon, not the MI pylon. Mostly they're using the Delta Sigma. And also the software, they're not using, actually the MI, they don't have RCS software actually. They purchase from the computer. They purchase from the Star Dynamics. So we now have a very good relationship with the computer. So we can together, and they are very good person, good engineers. We can provide, I believe, the best RCS system in the world, because actually F-22, F-35 are provided by them. And for the chamber engineering, that is, we are outsourcing, but we are design engineering. So we can design like the Huawei project. We build it, the Huawei project is a large chamber. We have currently the 5G. We have a 20 meter and 30 meter chamber, and very successful. We can have a third party doing the engineering, we design and doing the engineering, monitoring, auditing, and that work very well. Yes.
Thank you, Richard. Thank you. We are having one more question. So question is being asked is, what is the best cross polarization obtained in your large ranges?
If you want to have because we're using only single reflector, the dual reflector can compensate the polarization. That would be very good. But if the single reflector, I put it only to 30 dB. Yeah. Then we need a longer focal length, so the chamber will be longer, and the shorter focal length is the polarization will be smaller, but your longer one, yeah, will be better. I can send some test data. Recently, we are doing in the 5G for your reference. It is around 30 dB. Yeah, around 30 dB. I don't think we are not going to 40 now. It's only dual reflector to go to that. The 30 dB will be limitation. Definitely, like you can see this one is this FOD is only 1.2. Here is the 28 dB. Okay. On the edge is 28 dB, but it's 1.2. We can have 1.3 or 1.4. And then you can go down to the 30 dB. Yeah.
So anyway, everybody knows that for RCS single reflector is okay. But when it comes to satellite application, definitely we have to go for dual reflector compact ranges for the much better cross polarization. What is your experience as well as how many compact ranges you have delivered till now across globe? Single reflector as well as double reflector?
We don't do the double reflector. Currently, we only have a single reflector. We don't have we didn't develop the dual reflector, double reflector yet. Yeah.
Okay. So I think Manisha, you are having any questions? You have to unmute yourself, Manisha.
Actually, this is not much of my domain, so my knowledge is very limited here. So I think
okay, well, no issues. I think we have covered most of the questions. And thank you, Richard. So I think thank you very much for joining us and providing a very, very exhaustive information as far as RCS, angle of arrival and target detection measurement techniques are concerned. And I am really impressed with your that robo where you can simulate this angle of arrival so precisely that even in the of the order of 0.007 degrees. So which is, I can say that it is excellent kind of measurement accuracies, which I have never seen such kind of accurate system. We are having systems, but they are of the order of 0.01 and 0.014 kind of bore side determination accuracies, but your system is really good. And another very important thing what you have done is this, you have really reduced the cost of the HVAC system, because your reflectors can work in plus minus 10 degrees. So this is a huge relief for any organization, because otherwise unnecessarily we have to put a very, very costly as well as accurate HVAC system. And not only that, we have to maintain and continuously monitor throughout day or 24/7 that because most of the reflectors provided by other companies, it has to be ensured that temperature variation is of the order of plus minus 1 degree. So with respect to that, you are providing 10 degrees of margin, so which is really excellent. And I can see your cross pole values. And another important thing is you are having a single reflector, whereas other companies, they provide multiple segments and then they join it. And mostly in one polarization, inaccuracies comes because of those joints. So
Yeah.
I think those kind of accuracies also your chamber may not be having. So I can see several plus points from your design. However, yes, as you have rightly said that till now you are working only for a single reflector compact lens, which is okay for most of the defense applications. So
Yeah. So if there are any requirement, then we can discuss, and please send me the information to me and via the email. Then we can discuss and back and forth exchange the technical information.
Thank you, Richard. Thank you very much.
Thank you, everybody.
Yeah, thank you very much. And actually, our antenna team somehow was missing. Means could not continue here. They were having some other assignment. So any contact information is there, I would like to have so that I can pass it on, and later it can be Richard can be contacted.
Okay.
Thank you, Richard.
Thank you. So thank you.
Thank you, Richard. Thank you very much.
Thank you very much. So okay, I'm leaving.
Yes.
Then we try to find where I'm leaving. Okay.
You can just stop sharing.
Stop sharing. Okay.
Yes.
Oops.
So Manisha, can we go to our next presentation if you are okay? Again, you are mute.
Oops. Okay. Thank you. Bye.
Bye. Thank you, Richard. Thank you very much.
Yeah, actually, it's our list. People are
leaving. So no problem. We will end at this point of time, and then we can have some other day.
Okay. Or we give it whatever number. So I will pass
It is being recorded, but let us not disturb because from morning 8 o'clock people are there. So we will have some other time. Okay?
Okay, fine then.
Thank you very much to all that.
Thank you very much, everyone, all the participants. And thank you, Puneet. It was a nice session. And the SAR team was very much interested in that talk. And other two were good. Actually, I'm not directly related. But people who were listening, they were very happy with the presentations and the content. So now this particular session, since the antenna people were mostly not available, some contact information.
Anyway, we are having recorded. We will share with you. You can just share with you.
Yeah, fine.
Okay, thank you very much. Thank you one and all for joining us and staying with us till now. And I think we are having a very, very good participation from defense as well as space, both the teams. Thank you one and all. Thank you very much. Thank you, Manisha, for arranging everything nicely.
Yeah, thank you, Puneet. And thank you all the participants.